Okay, is this working? Yes. All right, I'm gonna call that a quorum. So welcome everybody to this session. First up, we have Julius Kronbiegel from Pumas. He's gonna talk about the advances in the Quarto engine for Julia.
Yeah, thanks. So my talk's titled Introducing Quarto's Native Julia Engine, Easier, Faster, Better. I'm a senior product engineer at Pumas AI, and let's get into it. So for those who don't know, what is Quarto actually? It's a technical publishing system, so it's supposed to help you create all kinds of documents based on reproducible code, markdown text, and code snippets that are executed, and the results of those are spliced into the final document. So it works like this. You start with some markdown document, a QMD file, a special markdown dialect that Quarto uses. You pipe that into Quarto and render it, and then the code cells that you've defined usually go through one of the available execution engines. So before there was a Jupyter engine for Julia, a Jupyter engine for Python, and a Knitr engine for R. And once your code is executed, is put together again with the markdown you've written into a final pandoc markdown dialect. And this is then piped to pandoc, which, if you don't know, is a tool that can convert documents from all kinds of formats into other formats. And this is then used to create the output files, which can range from HTML, PDF, Word, Reveal.js, which is what I'm using for these slides, books or websites. So the range is really, really huge. This tool has been around for a long time. So yeah, there's a lot you can do with this, and the focus is also on reproducibility, right? You don't want to create reports where you copy-paste your assets into it after you've rendered them in some other Julia REPL, but you would want to have everything in one place and be ready to go. So this is what a really small QMD file would look like. You have a front matter section, which you can define all sorts of metadata, like a title or which engine you use, which is the thing that I'm talking about. Then normal markdown looking text with your sections. The sections mean different things depending on what kind of output you have. Might be pages in a presentation, for example, or on an HTML page it would look like a normal heading. And then the code blocks that are executable are these ones with the curly braces. And you have a bunch of Quarto-specific options for those. And then you use your normal code in whatever language you're using. And whatever a code block returns is then used in a suitable format for the output, right? And that's the basic mechanism of it. And in the remainder of this talk, I'm going to talk about the engine for Julia, marked with the orange border here. And it says Jupyter here because that's what the state was before we got involved, right? And Jupyter, as you might know, is a Python tool. So there was always a strong Python connection in the way you had to use Julia with Quarto. And why did we write a native Julia engine then? Like why would we take the time if there was already a working solution? The main reason is the ease of setup, use, and deployment. So we just had a lot of trouble getting things to run reliably for our consultants. And it turned out that there are many pitfalls you can run into when you set up these kind of systems. Even though if they work, they tend to work well. Like, I don't want to disparage the previous solution, but there's just a lot that can go wrong the more moving parts you have in your system, right? And the other reason is that there are certain features. So Quarto historically came out of the R Markdown project, so it's historically very linked to R. So I think the company that does Quarto, Posit, was even called R Studio before, so it was an R shop basically, and you notice that when you go through the Quarto documentation, you notice that a lot of stuff, smaller but useful stuff, is only available for R because historically that's where it came from, right? And so for certain situations, we wanted to have the ability to add more features to the system, and Jupyter wasn't really amenable to that because it's just like it has existed in its state for a long time, and there's not really a way to add features to it easily. So that was the other reason. And I have the snippet here with Moses allowing where he said a couple of weeks ago on Slack, does anyone have an example of a presentation made with Quarto? Like I can't get it to work, right? Quarto check says everything is fine, Python works, and so on. When I try to render, there's some internal failure, like some model that can't be found. And then, without me even getting to it first, said like, oh yeah, I can just add engine Julia and everything works without Python. I'm happy, right? So that's great. That's exactly what we wanted to see. So I was really happy to see this on Slack right when I was preparing my talk. So yeah, I wanted to show like what could go wrong basically with the Jupyter engine. So this is just a small mind map kind of thing with the parts that you had to get right in order to render Julia stuff with the previous backend. So you installed Quarto, Julia, and Python. And then the question is, so you need iJulia for the Jupyter part, right? But where do you install it? It's usually recommended in the docs to install it in a global env, which I generally don't like. I don't like things that have to go in global environments, because the more you install, the more trouble you get into. Then in order to make things be picked up by Jupyter, you have to install or register the kernel. And this is another step that can go wrong, especially if you return to a working setup after some time, you have updated something in the stack, and then everything breaks. Sometimes hard to get it to work again. And you kind of have to repeat this process for every version of Julia, because every version needs another kernel. And then it just, yeah, it gets annoying after some time. And on the Python side, yeah, first of all, you need Python. So maybe some people who use Julia, they are not into Python as well. So for them, it's kind of a hassle to get anything to work on that side. And even if they have a working Python, then they still need Jupyter, which can fail, which was, I think, the reason in Mose's case. And even if they have Jupyter, like where do you install it? How can Quarto find it? What kind of env? I mean, there are so many things you could configure there. The same with Python. Like, do you have some global Python installation that's more likely to break over time because you install other stuff into it? If you have a local one via Julia, then there are also a lot of ways by which this can break. Environment variables you have to configure, all kind of stuff. So yeah, that's basically the picture you have for the native engine. You just install Julia, then you install Quarto, and that's it. So there's not a lot that can go wrong. So yeah, like the basic getting started guide for the native Julia engine would look like this. You install your Julia, you install your Quarto, you create a notebook where you specify the engine Julia setting, which I showed you before in the front matter. Then you add one of these curly brace code blocks. And when you then render the notebook, our package, Quarto Notebook Runner JL, is installed automatically in the background into an env that sits in a local cache directory of Quarto, so it doesn't interact with any other stuff, any other environment on your system. So I've basically never seen this fail. I mean, there are, of course, like with any system, systems can always fail, but this step of installing it and getting the basic thing to run seems to be very robust, and I'm quite happy about that. The reason you have to specify the engine Julia is that Quarto puts a lot of emphasis on backwards compatibility. So because the engines work slightly differently, they couldn't just make ours the default, even though for most users it should clearly be the preferred option, right? But nowadays, the docs should mention it everywhere. They put the engine Julia. And you can also nowadays put it into your project settings globally. So if you have 100 notebooks, then you don't have to add it to every one. Right, so the architecture of the system is shown in this little illustration. We have the main package, Quarto Notebook Runner, which spins up a persistent server process, which waits for commands from Quarto to come in through HTTP requests. And there are a bunch of these, like the main ones you're going to use is Quarto render, or a couple of special commands we've added in order to interact with the server process, like call engine Julia close to shut down a certain notebook that is persistent, or status just to see what's going on, how many notebooks you have, how long have they been running, stuff like that. Exactly, and these Quarto Quarter processes are always short-lived. It's just a command, and then they shut down again. So what stays in memory is this server process and the workers. And the server communicates with the workers through a socket connection. We were using Malt.jl directly, which is also what powers Pluto notebooks. But over time, we had to do too many modifications for our use cases so that we now use like a vendored fork kind of. For example, one thing that I wanted to mention here is that you can run different Julia versions on the different workers, and you cannot do this, to my knowledge, with Pluto because they use serialization for communication, and so this doesn't work across version boundaries. So yeah, what's Quarter Notebook Worker? That's like the package that we run on each notebook worker process that we spin up. It uses vendor depths to avoid conflicts with user code. So every package we use, we kind of pulled into the repo so that like if we use Bison, it doesn't conflict with any package that you might be using at some other version. And as we heard in the other talk before, there's currently no official way in Julia to do this other than copying the source and including it. So that's what we do. Then this package basically runs your code cells, and for all the MIME types that it wants to have from each output value, it turns that into a byte vector and sends that over. So there's only a small number of types that we need to send anyway, which is why we didn't need the serialization in the first place, like with which you could send anything, but we don't need to. There's just a really small number of things we want to send. So this package also has hooks defined, or you can define hooks in it for re-rendering logic. So the thing is, if you have a persistent worker process, because you want to be quick in re-rendering a document, right? You don't want to wait for the full spin up every time you do render. So these things wait in the background for you. But of course, like Pluto, basically, we have the same issue that we want to pretend like you're doing a fresh run every time, right? And this just has a bunch of difficulties. Like I was surprised how difficult it is to set up a system like this that reliably just executes code in a persistent process. So an example would be if you do one run in which you set like the black and white theme for Marquee, and the next time you delete it and you rerun it, then Marquee still has this theme set, right? And so everything would look wrong. And so you have to add kind of this stuff per package. Otherwise, you will just run into weird behavior. So that's like the just something you have to accept, right? There's no way around it. So for the packages that we use the most, we have defined integrations like that already. But it's also, and these are defined via package extensions, but it's also possible to do that yourself, but you have to kind of use requires. And the reason is that Quarter Notebook Worker is not a registered package. It's something that lives inside Quarter Notebook Runner and is like loaded dynamically into the process. So currently it's not registered, which means that you cannot define a registered weak dependency on it, because then the registrator will complain and say, like, I don't know this UID. Yeah, that's not ideal, but we have found that, I mean, the main drawback of requires, as far as I remember, is that it doesn't really work well with pre-compilation, but these hooks are usually tiny anyway, right? So I haven't yet seen a case where this was like prohibitive, and it's not the same as for official package extensions where you would really want to avoid requires. Yeah, so for the special features that I mentioned, that we, like certain cases that came up for us where we felt like the Jupyter backend didn't quite offer what we needed, I wanted to go over a couple of those. So one of them is the thing with the kernels. So we added Julia up integration, which means that you don't have to do anything else but adding like a small flag in the front matter to specify which Julia version you want to use. So this is really easy and stateless, so no file anywhere has to be updated or installed to make this work. It's just, that's all that's required. And what we do is we check that the manifest of the project that the worker process loads, that it matches the Julia version that you use. And we do that, I mean, it's not standard Julia behavior. Like in principle, you can load a manifest with a different version, and usually it will just warn. But we want to kind of force a better path to reproducibility and one way to do that is like to avoid mistakes like that, right? So yeah, we will just refuse to load an env which doesn't match the Julia version, which might be annoying in some cases, but as you heard also in the other talk, nowadays you can have multiple manifests anyway for different Julia versions, so that should not be prohibitive and rather be like seen as a guardrail kind of thing. So yeah, one feature which I find really cool that we have added is called cell expansion. Cell expansion is for dynamic document generation, so basically cases where you want to have the structure of your document depend on some kind of runtime information that you have, some kind of data maybe that you put in it. And the way it works is that you have to overload the Quarter Notebook Worker expand function for a given type that you have, return something called a Quarter Notebook Worker cell, or a vector of those, and a cell is supposed to be like a fake code cell plus its output. So as if you had written some code and that code had returned some output. And this whole system is recursive, so if the output of this fake cell again has something that is expandable, then it will happily continue expanding this kind of stuff. So it's not code generation, it's not like you're writing some kind of weird macro-like thing which writes code as if you had written it and then executes it, but it's all value-based, which makes composition much easier. And so to show what that looks like, here's an example. We are using the Quarter Tools package here, which is a companion package we also published, which just makes this, it's also called Cell, but it's a more convenient version of the same thing that you find in Quarter Notebook Worker. And as I said, Quarter Notebook Worker is currently not registered, so yeah, it's easier to go through this thing if you want to use this functionality. Here I'm defining a function which prints an info statement and it returns values of computation. And then I define one of these cells, pass the function to it. I do the optional argument, the optional keyword argument code, where I just pass in some string. And I also set some options, which is also optional. And these options correspond to the cell options I showed you earlier, like these specific Quarto settings you can add to a code cell. And if you then return such a cell in a Quarto Notebook Julia code cell, and the output of this would look like that. It looks like there had been a code cell written there, which repeats the code that was here, which was not actually executed, right? It's just, it's fake, basically. And the output of this function that's being run. So it captures the standard out or standard error, and it takes the value that is returned and renders that. And I mean, this 3 looks very, like, not very exciting, but imagine this function returns some kind of plot. Then it's really nice that it goes automatically through the MIME type display system, right? Because in other tools, as far as I know, usually when you dynamically generate parts of your document, you generate the markdown directly. At least that's what I usually see. And then it's more difficult because if you have assets, you have to save them somewhere and have space for them, and then take care that you integrate them correctly, and this might differ depending on the output format and so on. And with this system, you just return values as usual, and we take care of putting them into the document for you correctly. So the question is, like, why would you do this? This seems kind of arbitrary, this, this example. So on the next page, I'm going to show you a more useful case, more useful use case. So this is a feature that Quarto has, which is called a tab set. A tab set is just a way to show information more compactly, right? Like you have different kinds of something, and then you put them into tabs, and you can flick between the tabs, and this saves a lot of vertical space, right? And the way you usually do this is you define a pandoc div, which is this triple colon syntax with some kind of class identifier, and inside that must be markdown where you have a couple headings, and the headings define the tab titles, and the content of the tabs is then spliced into those, right? The problem with this is that you have to hard code it into your document, right? You have to hard code this fence and the headings and all the content, and there's not really an obvious way to do this otherwise. And we often face the problem that we have some kind of runtime data which we want to present in this way, but it would be very annoying having to generate this every time or to hard code it basically. And so how can we use cell expansion to work with this? We have a convenience object in Quarter Tools called tabset for exactly this purpose, but the implementation is really simple, and like you would have no trouble implementing your own things you want with the system. So I'm just defining a plot function here, nothing special, it just makes a plot and gives it a title so you can recognize it. Then I make a vector of pairs where the first element is the title of the tab and the second is whatever object I want to be the content of the tab. And when I pass this vector to the tab set object and return that in a cell in the Quarter notebook, then the output of this is basically this tab set with the 5 subjects that I have, right? And so this could be completely dynamic, like you can write a notebook that takes in the path to a data set as a parameter, and then you run this on some data set that has 25 subjects, then it works the same way as if you had 47, it doesn't matter, right? So this gives you a lot of freedom, and as you can see, you don't see any of the pandoc div syntax here, so that's a really common thing for people to waste time on, is to get these fences matching correctly, because in this document it can be really hard to see if you have 5 levels of divs, where the first one ends and the next one and so on. Like it's flexible, like you can write anything you want, but it's also hard to keep track of. And with this value stuff, it's much easier. And the next example I have is just to show the recursiveness of it a bit more, where now I'm not putting one plot object into the tab, but here I have 2 more helper objects in Quarter Tools, like markdown, cell, and div. And the div is basically what makes these fences appear that I was writing manually before. And I use a div and wrap a markdown cell in it, which is just a way to shortcut this output as is function of Quarto, which you can otherwise use, where you print text and then it's used as markdown. So this is like a more declarative version of that. And I have a div as well in this where I just put 2 random plots next to each other. And this div, I give another attribute, which is another Quarto special feature, some attribute called layout and call, which makes a column layout. And usually you would write that in the div syntax, but here you just put it inside an attribute. And when I render this, I get 5 tabs where each one has a bit of markdown rendered into like a bold text and 2 plots next to each other. So, and at this stage, that would be really, really messy to write in the normal syntax. So yeah, if you have ideas for how you can structure your documents in this kind of way, then you can save a lot of trouble by going through this object route. Yeah, that's the cell expansion feature. And then the last one I wanted to mention was R call and Python call integration. So our consultants sometimes want to show how the in-house solutions that we have written in Julia compare to something they would use previously in R or Python. And of course, you can use Python call and R call manually, but it's a lot of verbose overhead to... It doesn't look nice if you have like a string of code there, which is then formatted like a Julia string, so it's just plain green. It's nicer if the code that you want to show is R, is actually formatted like R, and you don't have all this boilerplate added to it. So what we do is, if you have imported Python call or R call, we use them to convert R code blocks or Python code blocks into all the boilerplate that you would normally have to write, and then these packages will be used to execute that code. And the nice thing about that is that you can interpolate Julia data into them, so it's usually easy enough to run the same algorithms on an array that you have constructed in Julia. So the most basic data types work fine with this. And then the output of this you can see on the right, where there's a plot from R, and Python is determining the length of the vector. With a little bit of CSS, I have added, because otherwise, like if you don't do anything, like you wouldn't immediately recognize what the language is that is happening in a given code block. But I've seen the other day that there's now a plugin for Quarto to make this even a little bit more obvious with like a a small box on top of it that mentions the language. So yeah, but as you can see, it's very clean. You don't see any of the boilerplate, and it's relatively easy to set up. Yep. So that's the last one I wanted to show. Thank you very much for your attention. So if there are any questions, I'd like to take them now.
I'll go first over here.
First of all, thank you for the talk. I think I've run into all of the problems you described with Quarto, so I really appreciate it. And one thing I think with like a notebook interface, sometimes that leads to a very messy development workflow. So like, I don't know if that's something you've thought about in working with your consultants, how to manage that at all, or is that something you think about? I don't know.
If you could elaborate what kind of thing you find messy, then maybe I can give a more targeted.
Yeah, that's fair.
Like, what thing do you find messy?
Hmm?
What thing do you find messy in the workflow?
Yeah. Well, I mean, I think some of that has to do with like the culture around data science, I think. But you know, I think I found a workflow where you work outside of a notebook and then get to the point where you're like describing the end story. Like you write a paper, you write a notebook. And that, yeah, I'm getting a little lost in that story. I'm just curious if you've run into that, like whether the ergonomics and like affordances of notebooks work well with like a longer development process. Basically.
Okay. Yeah, maybe I can mention, so one problem we run into is that the workloads that we often have in these notebooks, they are pretty heavy. So big models that are being fit and a lot of data being pushed around. And so one problem for consultants, which we are also still working on to find the best workflows, is how to cache the intermediate computations in a way that is easy to use, but also not so hard to mess up, that you're running something with an old version of a computation, because it could take a while to re-render a full notebook, even if your session is still persistent, depending on how much stuff you put in there. And we definitely sometimes run into this problem that the developers run a 10-cell notebook for testing, and then the consultants run a 1,000-cell notebook for testing, right? And then at some point things fall apart. I mean, they still work, but like the workflow becomes bad, and then you have to think about ways to mitigate that. So yeah, that's an ongoing thing we are working on, how to improve the workflows for our consultants. Yeah.
Thank you. I'm new to Quarto, so I apologize if this question's been asked and answered before, but is there plans or possibility of an interface for Pluto instead of Jupyter notebooks?
So this already doesn't use Jupyter notebooks. I mean, with Pluto, what you mainly get is the reactive execution mode, right? Like you're editing something, you save it, and then Pluto runs the cells that it needs to run. So it has its own persistent storage of the results you already have, and so on. So this is not really reusable for what we have. What some people have requested is a way to take the notebook that they have done in Pluto, because it's nice for development, and then turn it into something that Quarto can ingest. And that is a much, I think, a much simpler problem, because it's just about the format of the document. So if somebody was interested in that, I think they could make quick progress there, but we don't use Pluto, so we haven't looked into it further than that. But the only way in which we use Jupyter notebooks, I haven't mentioned it, but that's kind of the output that we create with Quarto Notebook Runner. Like in the background, what we send back to Quarto is an IPyNB file, just because it was a shortcut for development to reuse the post-processing pipeline in Quarto from what was there previously. Because I mentioned the R backend, and this one directly writes the markdown that has to go to Pandoc. So they have even more flexibility. And we've run into a few cases where IPyNB as an output format is a little bit limiting. just because of the spec of IPyNB and that it doesn't allow you to do everything you might want to do, but overall it was definitely a win to just piggyback on that and not redefine the wheel. Yeah.
One more.
Yeah, thank you. This is great. Two really brief questions. One is, I'm guessing this just works with Documenter Quarto. Have you done things with Documenter to generate this and using Quarto tools in that context?
I personally haven't. I think I've seen people on Slack doing it, and that generally seemed to work, yeah.
And then the other is, it looks like the Quarto devs have registered the very nicely named quarto.jl with a pretty anemic package. I'm just curious if you've thought about, like, the first thing I did when I sat down here is I was like, okay, I'm going to work with Quarto. I'm going to add Quarto, and that is not the right path. I don't know if you've talked with the Quarto devs, or it looks like that package hasn't been updated in a very long time. It would be kind of nice to just have a streamlined path there.
For the Quarto tools package, to use the name for that, or?
Or, I don't know, like just a high level, or something that might install Quarto for you, or something like that. The Quarto.jl package doesn't do much currently.
I see. Okay, so yeah, I mean the Quarto Notebook Runner package, you don't have to interact with at all. You don't really see it. Same for Quarto Notebook Worker, so we don't need the name for that. And then there is a Quarto JLL package, which in general works, but it did have a problem recently because of the read-only status of all the JLLs, and there was a small bug with that, which I already fixed, but you wouldn't get it yet with the latest version of the JLL that's registered, just because Quarto doesn't do backports usually, and so I'll have to wait for the next minor version. But that's the easiest way to get started. If you don't want to go to the Quarto website and download Quarto, you can download the JLL as usual, and then that will work, yeah. Yeah, I think Mose also did that in CI, and it was fine, right? Yeah, that was how that thread continued that I had a screenshot of here. So yeah, that's pretty nice.
All right, with that, let's thank Julius one more time.
Thanks.
Next up, we have Akio Tomiya, who's going to talk about Julia Quantum Chromodynamics.
Are there USB-C connect adapter? If not, I have that. Nope. Thank you. Okay, perfect. Okay. Okay, so thank you for coming. So I'm Akio Tomiya from TWCU, Tokyo Women's Christian University. That sounds weird, but in Japan, we have a lot of women university. And today I'd like to talk about Julia QCD, that is calculating subatomic world. So this is a self-introduction. I am a particle physicist, and I'm working for Lattice QCD, which I will talk about. And I personally working for kind of distribution of Julia in Japan. And I held several small workshops in Japan since 2021. And this is outline on my talk. So first, I'd like to introduce the Lattice QCD. And next, I will talk about why we make that new code. And third, I would like to introduce the Julia QCD and what it is. And I will mention to them benchmarks, and I will summarize my talk. Okay, so what is lattice QCD? So first of all, I should say something on the QCD. QCD is an acronym of the quantum chromodynamics, which is a fundamental theory for particles inside a nuclei. This is a theory for quantum anybody, and this is relativistic, and particles are strongly correlated. So that means that this is one of the hardest problems on the world. And why QCD is important? So QCD is very relevant to describe our world because that it is related to the origin of the mass. So our body made from atoms, right? And most of the mass of them are coming from the proton mass or neutron mass. And say proton mass is 2,000 larger than the electron mass. And the proton is made by 2 up quarks and 1 down quarks and massless gluons. But so mass of the quarks are very light. That is just 30 times larger than the electron mass. And actually, the mass of the proton is coming from the mass of QCD dynamics. So to understand that this original mass, we need to solve the QCD. And QCD is, how to say it? Actually, we cannot solve by hand, so we have to use the numerical simulation. And QCD is a theory, how to say it? To calculate QCD, we have to solve the 4-dimensional Poisson equation 1 million times to get one physical observable. So that is very hard. And core kernel of QCD is so-called D/. This is 8.4D stencil and bandwidth bound. And the dominant part of the calculation is a huge linear equation with D/. So actually, D/ is just a huge sparse matrix. We have to solve a linear equation many times. And scale of the computation is scale of the computation is very large. So lattice QCD accounts for the over 10% of the annual computation time on the leadership class supercomputers in the several countries. And across the HPC community, its computational footprints on par with the CFD and climate simulations. And this is a list of the users of supercomputers. So the top is at the Frontier in the US. So, and several groups uses this machine. And Aurora also in the US that uses the US QCD. And Fugaku is in Japan. And JQCD, PAX, and HAL QCD uses the supercomputers. So lattice QCD is a very important problem, and also requires a huge numerical resource. So I can say that the lattice QCD is a kind of Formula 1 in the scientific computing, because that it requires a huge numerical resource. And if we succeeded to simulate using one of numerical methods, using for lattice QCD, we can say that that numerical method works for everything. So it is important to work on the lattice QCD to establish new numerical methods. And this is a kind of a sketch of the what is a lattice QCD actually. And this is the integral on the top is that quantum expectation value. And this is nothing but just a multidimensional integral. So the size is 10 to 11. So that is hard to integrate by hand, but the computer can do that. And we evaluate this numerical integration using Markov chain Monte Carlo. And this is a sketch of the Markov chain Monte Carlo. First, we prepare the quantum field, and evolve using some numerical algorithm and get a new sample of that. And we repeat this procedure again and again. Then we can sample a lot of quantum fields. Then we can evaluate the quantum expectation value using these samples. And we use the HMC, hybrid Monte Carlo, or Hamiltonian Monte Carlo. This is a de facto standard algorithm to calculate QCD. This is just you can imagine that this is just a random momentum plus EOM. This is just a kind of Langevin motion or a random walk for the quantum field. And then if you get a lot of samples, we can calculate the numeric quantum expectation value using this equation. And during the Markov chain Monte Carlo, we have to solve this kind of equation. This is so-called D slash, and the dimension is 10 to 9, so that is very huge. But we have to solve this equation for each numerical step. So this is very hard. And outcome of lattice QCD is very impressive because that it can predict that which temperature will melt neutrons or protons. Or we can calculate the attractive force or repulsive force between nuclei, or we can calculate some candidate of dark matter. Okay, so this is the introduction of lattice QCD. Next, I would like to introduce the why we make this Julia QCD. So this is a kind of background. So lattice QCD formulated on 1974. This is actually last year it was a kind of anniversary year, and there are several codes written mainly by C++, as you can see. And so why we need to make new code using Julia? So this is the reason. So lattice QCD is one of the formulation for theory, but in physics we have another field, so-called experiment. And we have a lot of plan to future experiment that requires that very accurate number from theory. And but we actually hit to the some limitation for the numerical or hardware. So I mean hardware. So so we need to make a new algorithm to get the precise numbers. So recently we working on machine learning because that machine learning can use to calculate some numbers in lattice QCD as a surrogate model. And I mean, so we need to test the applicability of machine learning. But the problem happens because that lattice QCD is expensive, as I said. So that usually we use that Fortran or C++ to calculate these numbers. On the other hand, machine learning uses Python. That is, it has a speed issue. So of course we can combine them. But problem happens when we debug the code. So we want to perform simulation with lattice QCD plus machine learning without two-language problem. So Julia is, I think, the only solution of that. And why we make it with Julia? So there are several reasons, and I think that you can imagine that. So first of all, that Julia is LLVM-based, and it achieved that Fortran or C-level speed, preserving that REPL type interactivity. And also the good point of the Julia is that portability. So if you make a code using Julia, you can perform the calculation on supercomputer or notebook or laptop, wherever. So this is very convenient for me. And also rapid prototyping is very good feature of Julia. And also this is personal things, but many legacy code has a problem for the compile. So if you type make, then so you will see that the error message. So that is very hard for us. So we need, so on the other hand, Julia doesn't have such kind of thing. So this is, personally, I think this is a good point of Julia. Okay, next I move on to the introduction of Julia QCD itself. And Julia QCD is a name of the project and which has a lot of sub-packages. And basic stuff is a gaugefield.jl that's capable with the SUN, Lie group gauge field. And on the top of that, and we have lattice Dirac operators.jl that's capable with the Dirac operator, or D/, I should say. And we have QCD measurements that's capable with the measurement or calculation of the physical observable. And we have latticeqcd.jl. This is just a wrapper, but this is, how to say, which has a good interface, and also it has a good wizard for parameter file. So without any pain, we can start latticeqcd calculation using latticeqcd.jl. Okay, so this is a number of start history of latticeqcd.jl. So the number or users are getting increase and increase. And also the several studies are reported in the Lattice International Conference in the last year. And also, the Julia QCD gets some software award this year. So I think that so many people are, how to say, pay attention to this software. Okay, let me show the demo of Julia QCD or latticeqcd.jl. So install is very easy as other Julia codes, and without any problem, we can install the code and make a parameter file using parameter file wizard. Just type the run wizard, and there are two modes, simple and expert. And if you choose that simple mode, then you can just repeatedly type enter, then parameter files is automatically generated. And then you can start the calculation. So this is done in 5 minutes. So this is impossible for the other codes. So make takes many time, much more longer time than this code. Okay. And there are several works, but okay, thanks. And there are several works, but let me introduce my work. And I published one paper last year, well, this year, I should say. And we calculated topological charge of gauge ensembles. And this work has been done in more or less 1 month because of the portability of Julia. I can run the same code in different places. So this makes makes the calculation time shorter. So yeah. Okay, let me introduce the benchmarks. We performed several benchmarks for different machines. So benchmarks, number one is, this is my main benchmark. This is the calculation test for the GPU, CPU. And we calculated the operation of D/. This is just a matrix vector multiplication, but this is a good indicator of the performance. And we performed this calculation on Pegasus and Miyabi. Pegasus is the Intel Xeon machine with NVIDIA H100. And Miyabi is also NVIDIA machine, but the CPU is at Grace. And we changed that temporal direction size. And the benchmark 2 is for MPI, and also benchmark 3 also MPI. Difference of these MPI tests is at the machine. So we performed the calculation on Yukawa 21, this is Xeon. And benchmark number 3, we performed the benchmark on Wisteria. This is Fugaku compatible CPU. And the final one is that benchmarks on this machine to compare to the other code. This is the benchmark result. And the CPU execution time goes linearly with T. This is ideal scaling. This is okay. And also the GPU execution time stays on almost flat, actually. But the GPU version can be faster order 10 times. This is not reached to the hardware limit. This is essentially same plot, but vertical axis is the gigaflops. And with a single GPU, we deliver the equivalent of roughly 40 CPU cores. And the GPU, Julia QCD single GPU kernel not operating essentially at the practical performance limit because that it can be 10 times faster according to the hardware limit. Okay, so this is the second example of the benchmark. So we calculated inverse of D slash. This is done by conjugate gradient solver. And plot on the left is the absolute execution time, and on the right is the relative speed up for among the number of process using MPI. And you can see that it scales ideally and it works correctly. So MPI works correctly. And also this is a similar result with Wisteria. So this is Fugaku compatible one. This also works well. And the final benchmark is that benchmark on this laptop. And I compare with the C++ and Julia. And lattice size, the system size is quite small, but it scales similarly. So that means that Julia QCD is not so slower than the C++. More or less same speed, I think. Okay, let me summarize my talk. So Julia QCD is one of a package for lattice QCD, and it actually runs on any kind of architecture, Raspberry Pi or Mac or Fugaku or GPU machine, whatever, and easy to start. You can start in 5 minutes without any difficulty of compilation or build, and it has a good scaling. It shows good scaling for parallelization. And we implemented most of the modern architectures, modern formulations, and I think Julia is a good choice for most of lattice QCD researchers because most of us need a quick trial loops for the research. Okay, that's all. Thank you very much.
All right, we have some time for questions. Here we go.
Thanks for such an amazing talk. I was curious, have you been able to compare the performance of Julia Lattice against the standard C++ packages in HPC grids?
Mm? No, we haven't done yet. So this is just, yeah, actually that we have to, how to say, it is difficult to prepare the same algorithm and also same parallelization. So we need to do that, but it takes time.
I see, and there isn't any, like, I mean, I'm an experimentalist, so I'm not as familiar, but is there any standard benchmark, like calculating the pion mass or something like this, where you can have a direct comparison between how fast your code runs and how fast some previous C++ packages have been able to calculate a standard observable?
Let me see. So this code actually has a different implementation for several Lie group. That is actually essential. So it is difficult to, yeah, in some detailed reasons, so it is difficult for direct comparison between them. Yeah, of course, that if we, yeah, in principle, we can do that for some specific parameter regime, for sure. Yeah, in practical reason.
All right, anybody else? No. Oh, one more.
So you solve these large linear systems.
Yes.
Have you do you write the linear solvers yourself, or are there like packages in the Julia ecosystem that are like, that you pass your sparse matrices to, that then do the hard work of solving the linear systems for you?
Actually, good question. So in our packages, we use that linear solver a lot of places, and most of them are used that Julia, how to say, built-in solvers.
But you implemented them yourself in Julia. It's not like you're not using like the iterative solvers package in Julia, or there are a whole bunch of packages in the Julia
Yes,
ecosystem.
yes. So for example, to calculate the eigenvalue, we just use that RNOD. But most of them are, how to say, just use that linear solver.
All right. If there's nobody else, then let's thank Aki one more time. All right, we're gonna move right along. We have Jacob Krell, who's gonna talk to us about using Julia with the new hotness in typesetting. Is that what we would call it?
What was that?
We would call it typesetting, the new hotness in typesetting. All right, there you go.
Hello, everyone. This is Typestry. And so as a quick outline, I'm going to introduce what Typest actually is. And then we're going to get into the package itself with the command line interface, from Julia, how to use the package for types formatting, and then more generally types in the Julia ecosystem and future directions we can take this package, and just in general use types. So this is a relatively new markup-based typesetting system. It's just over 2 years old, but in that time, it's gathered over 44,000 GitHub stars. That is to say that it has a strong start and promising future. I think everyone who uses it and then is involved can see that. So that feels really exciting. It also exports to PDF, PNG, and SVG. The latest release really has experimental support for HTML and like very rough edges. And so each release afterwards, they're going to be adding more and more support. So over time, that will be fully fleshed out. So why should you use type? It has fast incremental compilation, good error messages, intuitive syntax, and is open source, free to use. They do have some paid features because they have a team, they want to make money, but they're committed to keeping the language and code open source. It's not for everyone. It might be too new, like it doesn't have some packages or some features that you need. For example, HTML support just isn't there yet. And again, it's only 2 years old, so it hasn't had the time to build up and develop its ecosystem. You might be wanting to write a paper and submit it to a journal, and it just says, no, we don't accept that. We can't do that. And you might just like LaTeX, and that's okay. I am unfamiliar with other, I never got super into LaTeX, so you might have some other reasons why you personally don't want to use this. Here are some examples of what it looks like. So again, it's a markup-based typesetting system, and this is an example of the markup. So we have like the raw text, we have different modes like markup, code, and math, different lists. Here's an example of their code. So in this first line, we have a loop, and in each iteration of the loop, we're leaving we're rendering some math. And then in the next one, we're creating a text box and coloring it with a color gradient. We can see that here. And I personally find this like easy to read and easy to understand and use. And it just looks nice. Here's another example of their math mode. This example is taken from their GitHub README. That's probably, like the image that this is part of is probably the best like elevator pitch, I'd say, for the language. So I'd encourage you to take a look at it. And again, it just feels readable, easy to use. I think we've had discussions in Julia about how like we want to write our code in as close to the formal languages as possible, and really close the gap between our code and the math and the domains that we're working in. And I think this helps out in that sense. So the origins for this package, I learned of this language, I thought it was cool, and I was like, well, what if we had LaTeX strings and LaTeXify, but for types? I think that would be pretty cool. And I saw a little bit of types in Julia at the time, but I thought it'd be fun to just try it out, see if we could get something going. And so here's what we did. This is a general structural diagram of the primary objects and functions you'd be interacting with in TypeStree. So in the top right corner, this types JLL.typest, that is the typest command line interface itself as a JLL package. So 2 years ago at the JuliaCon hackathon was when I actually first started coding this project and using that, just learning how to use that resource to compile a document, and then from then I've built the rest of the structure from there. So we're going to start on the right side, which is the command line interface, and then move to the left side, which is the types formatting, and progress from there. So this is the build tarballs file. So if types releases a new version and you want access to it, you go to this file, you update the version number, and you update the git hash, and if that builds correctly, then it will release a new version of types JLL. Myself and a couple other people have done that, but if we're ever slacking on it, feel free to. For example, if you're paying attention, you might notice we have not updated to 13.1 yet. So here's the command, which just wraps over this the command line interface, and it supports the general command interface. In the future, I'd like to add more methods for like abstract commands. The star here for implements means this is an unspecified Julia interface, so I'm just looking at the methods and doing my best to follow their implementation, and as an informal interface that's subject to change or possibly be implemented incorrectly, but it seems to work well so far. Also for these to-dos, you'll find several more of them throughout the talk, and if any of them stand out to you, feel free to tell me like, hey, I want that one, or just express your interest. You're welcome to talk to me about them. Yeah, I'd love to hear your thoughts. Yeah, so you can see when you run this help command, the output is from the types, the CLI itself. I've left out some of the output because it's too big for the slide. Then we also are able to construct that using a command macro. It works just fine. It's a bit primitive at the moment in that it doesn't have interpolation. The Julia's command interpolation rules are a bit different than the string interpolation rules, and I haven't learned what those are yet. So that is another to-do. We'd like to implement that, make it easier to use these command macros. And then I also ship the Julia Mono artifact so that you can render your documents using this typeface from Julia, and these are all the different ways you can do that. So the first one you see is the font path flag on the typist command line interface, and you can also set the typist font path environment variable to that. And if you don't, you can use the same for other fonts as well. So to go through the formatting side of the architecture, we're going to be implementing this example type for the formatting and see how that interacts with the functionality available there. So we have the struct JuliaCon. The purpose is just to define formatting for it. So we first implement types context, which is similar to IO context, where you're passing metadata to the formatter, and then show types, which is the formatter itself. You can see this you might think it could be easier to just do it through show itself rather than show types, but then you'd have to be unwrapping this metadata each time, and so I'm providing this to just unwrap it for you. You have the context available, and you have the IO, and you can go as normal. So you can see in this show types function, we're just printing hi JuliaCon, and then we're getting the year from the context. And this types context function that we're implementing provides a default value for that can be overridden in a couple of different ways, which we'll get to soon. So to start, now that we've implemented that, you can just call show types on it, and it will format it as we've defined. The default context can be overridden with both the keyword parameters, such as this year equals 2026, on the second example, and also, or by providing a types context, such as in the third example. Those two are mutually exclusive, just to make it a bit easier to provide that data. And then we also have a type string, which essentially it takes any Julia value that we have implemented show types for, and then formats it and holds it in the string. So we're using the show types method to print into the string here. And again, you can see that it uses the context in the same way as with show types, where you can provide a types context. You can also provide a keyword argument as well. In the second example, we see another type wrapping our JuliaCon struct. So this types text acts similar to text does in Julia, where text says it renders its object with print. And so types text, the implementation for its show types method is simply print as well. So that is a way to just reuse that, I guess. Yeah, and once again, we're using a string macro to construct these strings. So this is kind of a feature similar to LaTeX strings. In the first example here, you can see we're using the $signs, and that's not interpolation. So this string macro is very similar to a raw string, but it also supports interpolation. And you can see in the second example, we're using the backslash and parentheses to indicate that we're interpolating. And then it's formatting that as if you're doing a call to typed string. That's probably my favorite feature of this package. I know at least one person has disagreed with that, but I think it's just fun to use. The interpolation also supports escaping, as you can see in the third example. Render kind of brings the formatting and command line interface together as just a very convenient, easy way to take a value, format it into typed code, and then render that typed code. You can see in the first two examples, we're again using we're able to override the default context. In the third example, we have some options to specify what files are generated, whether it opens in like a default viewer if your machine has one available, and if it applies the ignore status flag to the command so that if it errors, it doesn't have a Julia runtime error. A little more info on the types context. So this is an abstract dictionary that implements that interface and iteration as well. And this numbered list here, this is the precedence for which context values take priority. So to start with, we have the types context or keyword parameters, which, like I said before, those are mutually exclusive. And if those are specified by the user or by a show types method itself, then we want that to take the highest priority. Secondly, we have a types context given in an IO context. That's also high priority because that can be specified by a user. But that first one exists so that even when you have this context in an IO, the show types methods are able to override that. Our third priority is the method we implemented at the start, which is the default context per type. And then finally, there's a default global context. So if you're implementing this for your own type, you can specify those defaults per type, and then typestree has this global context variable, as a fallback, and you're able to modify that to your liking as well. This is the default context, and they're used in several of the show types methods that I've been implementing for base, or like just types from base. So mode, let's see. I'm not sure we went over mode, I don't remember. No, I think we'll have a slide for it later. Yeah, we had the different modes in types. You have markup, code, and math, and the markup's the default. If you want to enter into code mode, then use the number sign, and if you want to enter into math mode, you enclose that in $signs. And so this can indicate to formatting like, hey, we're going to render something in math mode, but the current context is that we're in markup, so it'll put those $signs for you. But if you know, oh, actually we're already in math mode, then you can say it's math mode, and it won't do that. This preamble is used in a couple of areas. So there's some show functions that use it, and also render will put that at the start of every document that you compile to it. And again, you can just change this however you want. So if you don't like my preamble, you can set your own. This IO is used in show types to format the values. So if you need, it just lets you set additional default data there. But again, if you're passing the IO directly, then this isn't used. It's only if that's not present in your call. Yeah, this is a function. This method just lets you format a lot of values in PDF, PNG, SVG, and typed. I still need to add in the experimental HTML target. We might not, because that could also break notebooks if they prioritize that, and HTML isn't ready yet, so I might wait on that, but I should at least check it out. And I also need to test to see if these methods work in Quarto. But I do know that if you have something, if you define these methods and enter a value where show types is defined for it in Pluto or iJulia, then it will render it as per one of these formatting options. So these are optional, but I would recommend them if you are using this interface, because it allows anyone across the other packages to hook into this method without needing to know anything about typestring. And you don't even have to use my package if you just want to use these anyways. Like, just do it. The more types we have in the ecosystem, I think the better. So we have some packages with interoperability for types. This is actually a recent one. So we have a Luxor weak dependency that Chromolian implemented, and I think that's pretty straightforward. We also have types jellyfish, which if you were here last year, you might have seen. If typestry is the Julia to typest interface, then types jellyfish is the typest to Julia interface, wherein you can run and render output from Julia within your typest documents. So as you can see in this, in the final JL call, that is Julia code. And so the final output from that block will be rendered into your types document. And this doesn't know anything about typestry. It just uses the show interface, which is an example of why you should implement this. So any rules that he set there in his package, or any methods that you define that allow types formatting, will allow you to render your objects within a types document itself. This is the Julia side that you run in parallel to this types code, which provides the actual formatted results. We also have Makitech. I need to update the version but it allows you to use types in some of your figures and labels and titles, things like that. I think it's a bit more limited at the moment, but it would be interesting to see if we can get some better Mach integration in the future. These are other packages that know nothing about typetree, but they use types itself, and I recommend you check them out. This is something that I think would be interesting to do in the future that we don't have yet. So in LaTeXify, it has syntactic rendering, where you can give it an expression, and it will read that expression and render it accordingly in LaTeX. But that doesn't know anything about what that expression means. So you can see in this first example, you have y over x, and it just renders 1 over x. We're interpolating y in this particular case. And that is that is very achievable with TypeTree right now. It's not currently implemented, but I would just need to implement show types for Expr, which I hope to do Saturday. And something that would probably take quite a bit more time is semantic rendering, and this could be probably called like partial Julia to types transpilation, because if we're lowering to this types function and providing it with the parameters, if we implement the show types method that corresponds to that, then we have semantic information as well. So we know that in Julia, using the star or multiply operator on 2 characters combines them into a string. And in types, we can do the same thing, just with plus and strings instead. So I plan to set up types function just to exist. In terms of actually implementing the semantic rendering, probably wait until types releases a 1.0 and is stable, because that's a lot of work. Something else that would be cool is to do types Unicode completion in the REPL. This is a very hacky way to do it. You can do it. I'm not going to ship this. There's a proper way to do it. I need to figure out what that proper way is and then actually do it. But I think that would be fun. Types use different names for these symbols than both LaTeX and Julia. And yeah, it would just be cool to be able to use those instead. Another possibility is to use auto instead of these specific modes. So in this second example, I'd send the whole string to the types compiler, ask it what mode it's in, and then it would infer that for me, so I don't have to specify the mode is in math. And then probably the thing I'm most excited for, this was in a Julia discourse thread. As soon as they officially release the HTML target, I will be dead set on making it possible to do Julia package docs mostly in types, so you can be sure I'll be working on it if nobody beats me to it. So expanding man, I really looking forward to that. We just gotta wait for HTML to be finished up. And that's, final thing, these slides were written in types. Any questions?
Do you have any questions for Jacob? Yes.
Hi, thanks, fantastic talk. This is really exciting. I use types a lot. For some use cases where you need individual glyphs rendered from text, do you know if that's something we need to have like a wrapper around some internal Rust APIs to be able to get, or that's already available from command line somehow?
Are you talking about like entering the glyphs themselves, or like the name of them, like such as with this?
The glyphs themselves. So for example, in Machia, right? Like we have the way to render like a whole document kind of thing and then put it somewhere. But imagine you want to use the rendered glyph as a scatter symbol or something. Makia needs the glyph baseline, heights, whatever, so that they can dodge each other, for example. So you need individual glyphs things. So Makia can do the kind of layout. Do you know that information is available somewhere?
Let's chat after.
Okay, cool.
Anybody else? So calling expanding man's bluff is what you guys meant to be that documenter you write in Markdown and then it targets types instead of HTML, or you write in types as part of?
I think the goal is that your doc strings and your doc strings can be types themselves, and instead of writing Markdown files, you're just writing types files, and that should integrate with Documenter.
Perfect. All right.
But I'm not expanding man, but that's what
I know you're not, but
yeah, that's what I would like to see.
Whoever they may be. Okay. All right. Good. If there's nothing else, let's thank Jacob one more time.
Thank you.
Okay, to finish this session. Y'all are making it easy for me to keep time.
Okay. Do I have battery? I do, okay. All right. So, let's see, this is not quite working yet. There we go. Cool. Oh, yeah, I can wait for a bit. Yeah. So I did want to address that question about types working in Documenter, because my talk is about Documenter, and specifically how you do crazy shit with it. And so the thing with types integration, right, is that the way Documenter works is that it's a Markdown to Markdown pipeline, and the parser and the AST structures that it works on are Markdown. Could you create a parser that parses types and gets it into the AST? Yes. I don't think that would be particularly easy to do, because the types, I don't know what the types representations of things like code blocks look like, right, for example. Now, getting Documenter to output to types, it would actually be not so difficult to do. And so I'll show sort of how you do it. But yeah, just let me know when I should start. Or if anyone has any other random questions, I mean, we have a couple minutes, so. Actually, just out of curiosity, how similar would you say like the types syntax AST is to Markdown? Like not the syntax itself, but like the structure of the document and the AST representation. Oh, sorry, didn't mean to make you run there.
Structurally, I think there's similar elements if you're staying within Markdown mode, but I think it diverges quickly, and the internal representation is very different.
Yeah. Well, I mean more the structure of the document, right? So like in that you have a header, and then you have some text, and then you have some like random like code or elements or whatever, right? But like, I'm guessing they're all kind of similar LaTeX types, like just the structure of the document. Like, you don't do crazy stuff with HTML or like HTML does or something, for example.
You can.
Oh no.
Yeah, it is more complex. It's a full scripting language in it. It wants to have feature parity with LaTeX, other powerful editors.
Yeah. Okay, interesting.
All right, so now it's officially time to start. So again, last session of the block, we have Anshul talking about Documenter JL.
Yeah, hi. So I now work at Julia Hub. I'm also one of the authors of Documenter VietPress.jl. You guys may have seen that. did a bit of work on Documenter, a lot of work on Market.jl, so that's the sort of primary open source thing that I do. But yeah, today I just wanted to sort of demystify a bit how Documenter.jl actually works, because it's a very powerful tool that I don't see people using its power that much. And I've done some crazy stuff with it recently, so I thought it would be a nice opportunity to just show how you can do that too. So first, what is Documenter, right? Documenter is a documentation for Julia. It takes in Markdown input, and it can give you back, by default, HTML or LaTeX. With some external libraries, it can give you Markdown output too. But that's not the whole story. The whole story is that this is a Markdown-based processing system. So what do I mean by that? I mean that it reads in Markdown files, right? And so I have a little demo thing here. This is kind of too zoomed in. Is this good? Yeah, all right. People can read this text mostly? Okay, sweet. Yeah, so you know, this is your classic docs directory, right? You have a make.jl, which you have some make.docs call, right? And a lot of this is kind of magical, but implicitly it will assume that your source folder has some Markdown files. And you know, you can have some Markdown files, right? And you know, maybe we can have a file that has some problems, right? In here, you'll note that I have not closed this triple backtick. And what it will do is it will load these in, it will parse them, and so doc.user.pages. Oh, did I not run this in this session? I guess I didn't. My bad. Well, it'll run at some point. But what it'll do is it will parse the pages. And okay, so you're all familiar with this, right? This is sort of the standard thing you see whenever you run Documenter. Oh, it's running through all of these things. It's setting up the build directory. It's running doc tests. It's expanding templates. But what all this stuff actually does is it manipulates a Markdown abstract syntax tree that's held in memory. And so if I look at doc.blueprint.pages, only... Oh, okay, that's just a spec, never mind. Doc. Where did that go? You can tell that this is sort of on the fly. I'll find it at some point. But basically, if I print out this doc, you will see this thing, right? Specifically this thing. And so you see that, there you go. So it's this dict. And so this is the home page, right? And so it's automatically picked up the header, and it said, okay, the file is build/index.md, or that's where the file gets built to. And what you have in there is this markdown ast.jl abstract syntax tree. And so in this case, it's just got a single heading, right? It says markdown ast.heading level 1. And within that, it's got this text element. But this can be nested arbitrarily, right? You can have text inside of which you have links, or you can have a paragraph. You can also define your own nodes. And so this is what I mean. It's a very flexible system. This is what I mean by the abstract syntax tree, the markdown-based processing, right? And so why would you want to hack this? What could you possibly do that Documenter does not already do for you? It turns out you can do a lot. So one example is example galleries. So I have this in geomarket.jl, which is another package that I do. This is also Documenter VPress, so that the thing looks slightly different. But by the power of modern web technology, I'm going to zoom in. And so you can see that, okay, you know, this has got this, if you're familiar with democards.jl, this is very similar. You know, you've got these examples. It pops up some stuff. This is all HTML, right? The real trick is in writing the examples itself, because the idea is you want to make this as easy to use as possible. So if I go to the GitHub repo, which I can't actually reach from here, there we go. I have this examples folder, right? And in that, I just have these literate.jl files, which have these little code blocks, which actually execute inside the same process that runs all of this. And so the cool thing with this is, the reason I built this is because I saw demo cards. Demo cards is great, right? It's got a lot of cool features. It does Jupyter notebooks and all that stuff. But I saw demo cards and I said, hey, I don't want to save stuff to files. That's like so annoying. And so how can I not save stuff to files? How can I do this manipulation programmatically such that if I say that there is a cover image, right, I can just pass a marquee figure, I can pass a plots.plot, I can pass anything I want. And you can multiple dispatch on this package that I've written and make it such that whatever you pass here can be translated to an image, right? And so you can do that. And then what this also does is it says, hey, you've got a cover. Let me inject that right here. So it injects that into the Markdown syntax tree while Documenter is processing this. And then when it writes it out, right, you'll note I never included this figure. I never said anything about this thing. But because I wrote this extension, which automatically added this here, I don't have to worry about like a nice preview image for my blog post. So that's one thing. The other cool thing, okay, so look at this, right? This has the, I think I might have added those explicitly to everything actually. But I could also remove this title, right? I could remove this completely. And what it would do is it would say, okay, let me find the first H1. Let me find the first top level heading. That's my title, right? And so you can do all of this programmatic processing inside Documenter and make your life just so much easier. So that's one thing that you might want to hack it, right? Another thing that I did recently for Julia Hub is we created this new language called Dyad, right, for modeling, and said, okay, we want to document this thing. But the way that the Dyad language works is that you write some Dyad files into a package structure, and then you run the Dyad compiler on that, which will transpile into Julia code, right? And so then you load that Julia code into a module, and then you have those available as modeling toolkit models, right? And so all of this to say that these things, this Dyad code has a very different way to run it than the Julia code does. But they both have to be integrated, right? The Dyad code has to feed into this example block. And so the way I do this, which I'll go over, unfortunately that repo is not public, but I can show it to you on the video, so I'll do that. But the way we do this is we literally just created a documented processing pipeline that goes into a page, takes all Dyad blocks, compiles them, and then into every example block, it injects a using statement, right? And it hides that from the user. And so I can just write this, it will just work. But if you look at the code that actually gets executed, it's got these things which are programmatically added into it. Another thing, so maybe I can click on this. Yeah, okay, so this is live, right? And so I kind of just edited the HTML here to make it nice to show on a slide. But here you go, right? You have this analysis world, and you can see that WheatPress has this nice feature. It'll show you the language name. But here's your model, right? And here's this thing called an analysis, which you're running on it. And then in Julia, we show that you can just literally do using plots, plot result. But this is implicitly using the package that was generated by these. And so that's all in a Documenter pipeline. You don't have to think about it. You don't have to worry about it. You just have to write your example, right? And so what I was talking about with this example thing in Geomarchy was the dynamic rewriting at build time, right? So it fetches in-memory objects. It can use them, do whatever it wants with them, really. It can rewrite any aspect of your page if it wants to. And so how it works, as I showed, this is sort of an example from Markdown AST.jl. You just have this tree of Markdown syntax, right? And this is sort of a flattened view, but yeah, I mean, this is sort of how it works. So let's say, for example, that you wanted to mutate a Markdown AST. This is a super simple way to do it, and I'll actually run this in a bit. But basically what you do is you can do markdown.parse. There's a typo here, whoops. But you can do markdown.parse, right? That gives you a markdown.md object from the Markdown standard library. You can convert that to a Markdown AST.jl node. And once you've converted that, this is then completely compatible with abstracttrees.jl. And so you can just run a depth-first search. If any node you encounter is a link node, you rewrite the link, right? If, for another example, we had some malformed SVGs being generated, right? if you go through the markdown, which is of course parsing as markdown, and it's not parsing as XML, right? That whole thing is just one paragraph block. If you go through the markdown and you see, hey, this is a malformed SVG, delete it. It's gone. And notify the user and all that, right? So I show this just to show how you can use Markdown AST. This is not to say that you have to run markdown.parse on every page that you have, right? Documenter does that for you. It has a lot of hooks by which you can hook into the system. And it's a pretty flexible pipeline. So instead of writing up random slides about it, I will just show you the code. Is this sort of visible? Perfect. So this is the cool stuff, right? So you'll notice these names look very familiar. Set up build directory, doc test, expand templates, check document, right? And so what all of these these are stages in a pipeline. And this pipeline is what Documenter runs from start to end. So initially, it will set up your build directory, right? It will run doc tests. This is the magic. This is where the magic happens with example blocks, with your page at meta blocks, right? With your setups. This is where the magic happens, is expand templates. Because in there, what it will do is it will search for any markdown that looks like this, right? That matches some criteria that you as the user can define. It doesn't have to start with an add. It doesn't have to be a code block. It can be whatever you want. But it will use its own matching engine to go and find these things. And then it will provide them to you in a function that you can just, you define a subtype, and you can just write your dispatch of that function and perform whatever manipulation you'd like, right? So another stage here, it finds each atref, and it goes and finds the correct cross-reference, and it sets that link, right? This is like the very, very complicated version of that little link rewriting script I showed you guys earlier. Then this thing will populate the tables of contents and the indices with links. This render document is sort of where you write that markdown AST to some file, right? Whether that be HTML, LaTeX, could be types. I wrote a library I rewrote the library that sort of bit rotted, that does it in Markdown, so I still have to merge that PR. But so basically how this works, how you set this up, is you define, you create your abstract type, right? That subtypes Documenter pipeline. And you define when it should run. And this is a floating point number. But so let's say that you had some processing pipeline that you want to run before you expand your templates, before you call your example blocks, right? This is the case for that dyad thing I showed you, because you have to actually load the Julia library, so that actually has to exist. Just define it as just define the order as 1.9, right? If you have something that's going to add new cross-references, define it as 2.9 before 3.0, so on and so forth, right? And so this matcher is just generally true. I mean, you can make it generally not true, but there's not really a point, because this only dispatches on the document. And so the next thing that you do is this selectors.runner function. And this is where the magic happens, right? This is where you do the processing. So let's see if I can find maybe a simpler example for this. So I haven't published this package yet. At some point today I should do that. But let me see here. I think I had a short-ish build step. Yeah, this is kind of all right. I can probably explain it. Okay, so this is in ohmycards.jl, which is the library I use for those demo cards in Geomaki, right? And so what this is doing is it moves all of the card meta blocks to the start of the page, because we want to the end of the page, because we want them to be processed by expand templates after all the example blocks have run. So the processing is not, it has a very strict order, right? It goes from the top of the page to the bottom of the page. But you can change the order. You can change the AST as you like. And so this adds a example block if requested in the pipeline, and if you found this adds the cover block and all of that stuff, right? It adds badges to the pages. It could add badges to the pages if we wanted to. I didn't implement that yet. It also adds the page to, it manipulates Documenter's expansion mechanism to say that you should always expand this page first. The reason for that will become clear in a moment, but it's basically because I am also, the way that those gallery blocks are generated, it's not manual, it's actually also just a documented block. But in order for that to get generated correctly, you need these card meta blocks to be run first so that it populates the document with that knowledge. That you have certain examples, and this is where they are. So okay, so what are we doing here, right? We've defined this example processing thing, we've defined the order, right? So it runs a bit after doc test, a bit before expand templates. And we've defined this, our own selector function, which just checks, hey, is this element a markdown code block? Does the card meta, its language, does it start with card meta, right? Is this something that we care about? And so what this is doing, first you get the settings, and the settings are this example config, which is basically just a way for you as the user to pass information to this build stage. And so this just gets put into the plugins keyword argument to make docs. And I'm just iterating over each page, right, in doc.blueprint.pages. This is how you do it. I forgot about that. And so what you do is you say, okay, find all card meta blocks in the page's markdown AST, right? If the page has a card meta block, is it a known example page? As in this case, I kind of hard-coded that to say that it must occur in an examples directory, but I should probably change that, right? This could be any predicate function you want. You can also set known examples in there. But even if it either has a card meta block or is a known, if it's a known example page, it will generate the card meta block, right? If it's not a known example page, it won't. It will assume that it either should not have a block, or if it should, then one should exist, right? The user should define that. If it's not, then you just skip that page, right? You move on to the next one. Now, this is where the cool stuff happens. If there is a card meta block that was detected, you insert that after the last element in the page. So you've found this block, and you've mutated the AST such that it gets inserted at the end. And the reason this runs at the end is because all of your examples should run before it, right? And if it did not have a card meta block, but you know it's an example page, well, then you generate this AST node, right? And you insert it at the end. And so, yeah, then after this, this is all kind of useless. I mean, this was stuff that I wanted to do, but I never ended up doing. This comment over here. But yeah, so this is the last thing, right? It says, okay, if this is an example page, if the file name is not in doc.user.expand first, we make sure it's there. Oh, thank you. Oh wow, okay, oh my. Okay, so let me sort of speed run this thing. So this is the build stage architecture. This is the plugin architecture, right? You subtype document.plugin to create the info you need. You subtype the document to pipeline stage to get a build stage. And then you have a user, if you want to communicate, you just have a user pass an instance of that type. Okay, so let's go back to ohmycards.jl, because there's one more thing there that's pretty cool. Did I lose the window? Oh, interesting. Okay, so if I go to this thing, which is the overview gallery block, what this is doing, or maybe I can show this in Geomaki actually. Let's see. Examples.md, there you go. So if I look at the code here, you'll notice that there's this overview gallery block. And here I'm just listing out the names of the examples that I wanted to show in this block, right? So it takes these, and it says, okay. So this is an example of the sort of higher level API, the document, right? Like what I showed you was the very low level, you do everything yourself, but you can do what you want. This is the higher level API where you define a documenter matcher, where it will say, hey, is this a code block? Is this not a code block? Does it start with overview gallery, right? And if it does, then documenter will invoke this runner function. And so what we then do is we say, hey, okay, for page name in every line that's contained within that code block, you obtain the element, right? So you find the page name from the known examples. And this is what I use the plugin for as well. The plugin has a dictionary. And so you store every example in that dictionary. And you get that out here. And then you say, okay, what's the path to this element, right? What's its cover, what's its title, what's its description? And you push this HTML that I generate into, well, that's just pushed into this array for now. But this gets injected into a grid container, and it's got some CSS. And then you set the actual contents of this node. You remove the code block. That's gone. Now it's a raw HTML node that contains this HTML, right? And so of course this only works for the HTML back, as long as you're in some HTML-like backend, right? But you can see how you do this, right? You can see how you say, okay, when I see this block, I want to do this, right? And so this is sort of the core of Documenter extensions everywhere. If I look at Documenter-mermaid.jl, which basically lets you use mermaid diagrams in Documenter, what you can do is something like, let's see. Oh, it's all in here. Wonderful. So they've got this mermaid block, right? And here what they've done is slightly different. They've said, hey, they've overridden the specific function from HTML writer, which I don't recommend you do, but you can if you want, to say, hey, if you are the HTML writer and you see this mermaid block, right, just define a div class equals mermaid and put the code in there. And then for every page that has such a block, it will insert the script that runs and loads the mermaid library. And so this is the build stage that just inserts this mermaid script block onto every page. So this is like a super simple thing that has just been done. One thing I did want to show really quick is the dia documentation that we built out. And so this has a lot of stuff, right? And so one of the things that I did, which is not quite Markdown related, is I figured out how to hack the Documenter navnode system such that you can have a clickable high-level entry. So, and really we need a better API for this in general. But it turns out you can just do this. And so what this is in Documenter normally, you could not click on this and get a separate page, right? This is just a text. But with this, you can inject so this can be a top level thing, and this could be one of those ohmycards.jl galleries that I showed before. This could be anything, but this comes in quite handy in the dia docs, where you may actually want to click on a higher level thing, and I don't actually think I ended up using that anywhere here. I did here. So you can click on this, right, and this takes you to a sort of home page, and then this is just an index with a lot more information that gets auto-generated. But then you can also go here, right? And these are subpages which tell you about it. This is in particular a partial sensor. It's the API for a sensor, effectively. So yeah, that's most of what I wanted to cover, I think. Thank you all for listening to this talk. Please descend the ladder of madness. But yeah, thank you.
We have time for questions. Oh no. There we go. Thank you.
How much of this is in the Documenter API or is liable to break?
So Morten has assured me that this will not break. That being said, it's not formally API. We both agree that it should be API. And so if people actually want this, then message on the documentation Slack channel that we should have an API for this stuff, and we'll figure that out. But I think in general this is sort of set, right? Like this has been set since Documenter v0.20 something. I don't think it's changing much. I will say that the Markdown AST stuff is actually a formal API. But the Documenter selectors thing is also kind of, set in stone, yeah. I haven't had, for what it's worth, I don't think I've touched that ohmycards package in a year, and I don't think it's had breakage. It's running on the latest Documenter version, it's fine, so yeah.
Any more questions? No.
Hi, simpler question. So for Documenter, a pet peeve of mine is on the side windows, the quick navigation bars. Is it possible to have number sections? Because right now it's always non-numbered, and I couldn't figure it out.
Do you mean here?
Yeah.
I think you could write a build stage to make them numbered automatically. You're asking specifically about automatic numbering, right? Not, not like manually. You can always just do it, right?
Of course, I don't want to do that.
But it's possible through a very similar API to this special page node thing. You just define you define a page node type. You define documenter.walk nav pages on it, which basically just has to recursively go to its child pages, right? And maybe you push some nav node to the internal nav list. This is also in documenter pages.jl. It's not that this is like only private code that I cannot show to you. But then what you do is in make.jl, oh, this is the other cool thing I should show off, but later. Somewhere in here, one of these things will be a special page node. You construct a special page node and you pass it to that array. Oh, sorry, no. One of the limitations of Documenter right now is that this pages thing has to be a vector of any. And so you can wrap this all in the special page node. And the special page node can then dictate your behavior and have its own strange child types and whatnot.
Okay, if you have spare time, if you write a tutorial on it, I will be
I should, well, it should be part of the Documenter pages documentation on how it actually works. So at some point that'll go there, yeah.
All right, great, thank you.
Yeah. While you're walking, one thing I did want to say is that you can also choose to not build a document. The way you choose to not build a document is you pass format equals empty array, and you will note the very emphatic note here. And then what you do is you empty the format, you push to the format whatever kind of format you want, right? And in between those, you can edit the AST. So I have one internal side that we use for previews and then one production side. And I change certain things. I change like the edit link or something, or the GitHub icon between those. And then you call documenter.render, then you deploy docs. Then empty the build folder, empty the doc format, push the new format, call documenter.render, call deploy docs. So this is also a cool thing you can do. Right, sorry, someone had a question.
So this might be a little bit out of scope, but I was wondering, like, are there plans to add support for to document other programming languages like MATLAB or Python, similar to like Python Sphinx? Or how would I go about hacking Documenter to make that work?
Yeah. So you could do something like what I did here with this @dyad block, right? Which this is also just executing code. Where did that go? This is also just executing code from a different language, right? And so if you wanted to tie them together, there are ways to do that through Python call, rcall. I don't know if the MATLAB library is still sort of working or not. I don't think the Documenter is ever going to, like, I don't think that the core Documenter developers particularly want to support other languages that well. But if you have a driving use case for it, I will say it's not that hard. So.
I had a practical question, so it may be also beyond the scope of your hacking Documenter. But one of the things, I mean, you have a huge project, right? Diet is an enormous thing. If you change anything, right? So we are struggling also. We have a big project with big documentation, and you change something, right? And you want to run the Documenter itself, or you want to run test suites individually. We always have like multiple environments, and it's just very messy. And often it doesn't work, and the paths don't work. So is there a solution, a simpler solution to run this by hand, run this over the CI?
Because,
I have a solution
for you.
It looks so simple. When you do this, it looks so simple, and then when I do it...
Yeah, no, I know exactly what you're saying. So we had a similar issue internally. And the solution to this is you delete everything in the pages. You delete all of these entries. You only put the page that you want to change. And then you say pages only equals true in make docs. And that will stop Documenter from parsing anything that is not in the pages array, which happens to contain only one thing. This is like a very local development solution. For CI, one thing you can do is that I do sometimes do, the document at meta block evals in the main module. And so what you can do is, in every page, you can dynamically add a meta block that checks for the presence of an environment variable. And you can say, I'm just going to write it here. Right? And so you can do that, and that'll automatically be converted to a draft. And in the PR, in your GitHub workflow, you can add certain environment variables depending on the presence of labels. So that's actually what I do for this. The full documentation build takes like 2 hours. On the PR, it takes maybe 1 hour. But I could push that down more, but yeah.
All right. If there are no more questions, we are technically at time. So let's thank all the speakers of the session. Go have lunch.
Thank you.
CI is always green. No, it was gray a bit ago because I hadn't edited this package in a year because it worked and nobody complained. So I just left it be. Then I wanted the light to be green instead of gray, and so I had to run CI again. And I did. And it passed just in time. Okay, it's 1:30. Yeah, so that's about it. Constant time, discrete random sampling. Any questions? So I'm just going to start out by demoing this because I think that's the best way to show an API. I can create an alias table, and I can give it weights, like 0.3, 0.6, 0.1. And if I do this, now I've got this alias table object. And that's quite a big printing. And those are printing unsigned integers because this thing represents things internally with unsigned integers, and that's the precise probability distribution. It's hard to represent probability distributions exactly, so we just round to the nearest 2 to the negative 64th, which is typically good enough unless you're running a very long experiment. And now if I sample from this using just, the normal random API, I get a 1, a 2, I should get some more 2s. Oh, a 3, that's unlikely. Not getting very many 2s, Randomness is hard to demonstrate, hard to prove. And I can do if I wanted to draw 100 of them, works like that. Just uses the normal random API. So that's all you need to know to use it. And you need to know that it's O of n construction time, which is the time it takes to read the input, and O of 1 output time, which is the time it takes to, you can't beat O of 1. Great. So that's the API. And now, if you want to know more, you can read the docs. The docs tell you more. Shout out to Documenter Vitepress. Okay, so now I want to talk about what the deal is with discrete random sampling and a series of algorithms, and just kind of showing a progression of algorithms, and then I'll dive into exactly the implementation that aliastables.jl uses, and then we'll have time for questions. So that'll be the rest of the talk. Starting off, looking at this implementation. This is a linear time implementation. It's just a simple loop. You loop over the weights, and the weights need to sum to 1, and describing the algorithm is hard. So if the random number is 0.5, then as you go through the weights, you first subtract 0.3, and that's not less than 0, and then you subtract 0.6, and that is less than 0, and then you return 2. And if we look at the weights as broken down like so, 1, 2, 3, 0.3, 0.6, 0.1, that r equals rand is like picking a point between here and here. And then the algorithm loops through the buckets and lets you know when you've gotten to the bucket. So based on that intuition, it's correct up to floating point error. Great. Now that's linear time for sampling and linear time for construction. I guess you could call it O of 0 for construction. I don't know. It's pretty quick to construct, but O of n sampling is kind of a bummer. So we can compute the cumulative sum and then do a binary search. That gets us down to log n time, and it's O of n setup. And again, it's picking a random thing, a random point between 0 and 1, and going to the corresponding index. But the algorithm is binary search. I'm not going to go much into this. This is not what alias tables uses. Okay. Alias table, O of 1 random sampling, and it's a really simple algorithm. And simple is good because simple is fast. So here we have this accept and alias, and yeah, we're just gonna take for granted what the accept. No, yeah, I'm sorry about that. So I want to start with the sampling method first, and then get into construction. Because I'm prioritizing runtime of sampling, so I want sampling to be simple and efficient. And this is not my work. This is, what's his name? Alistair Walker made this in 1977. So nothing new so far. And when we sample here, we're taking a uniformly random index between 1 and 3, and then we're redistributing some of that weight. So to draw a little picture, we start with uniform buckets, because sampling a random uniform number, oh, that's not uniform at all, is fairly easy. Sampling a random number between 1 and 3, uniformly at random, it's O of 1. It's not super fast, but it's pretty good. And then from this, they each have a probability of 1/3, which is wrong, because we want 0.3, 0.6, and 0.1. So we need to redistribute some of this probability. And that's with this, that rand is less than except. Oh, return 0. That's supposed to be return I. Silly goose. Oh, sorry about the confusion there. So if we set all of the accept probabilities to 1, then this is just taking a random number between 1 and 3 and returning it. Pretty straightforward, pretty fast. It's wrong, which is unfortunate. So we need to set some of those accept probabilities below 1 in order to distribute the probabilities properly. So if we start, for example, by looking at this, this 0.1, we want to be distributing only 0.1 here, but we're actually distributing 1/3. So what's 1/3 divided by 0.1? It's about 0.3. That math was not quite right. Anyway, so if we accept only 0.3 of this 1/3, then the total acceptance probability is 1/3 times 0.3 is 0.1, which means there's a rejection probability of 0.7, meaning we have 0.7 times 1/3 probability of going to wherever this alias points to. That's return alias of I. So alias of 2 in this case, let's set that to 2, because 2 probably needs some more bonus points. It wants 0.6 and only has 1/3. So we'll set the alias, this is the accept, and the alias will be 2. Great. And similarly for here, 1/3, we want 1/3, or we want 0.3 probability, and we've got 1/3, so we need to set the alias to 0.9, or the accept to 0.9, and that way we'll be accepting a total of 0.3, and we've got a little bit left over that can go to 2, and then by conservation of probabilities, because we're not destroying probabilities, we're not rejecting ever, we're just redirecting, we know that this is going to add up to, because this is 0.3 and this is 0.1, we've got 0.6 left over here, if we accept 100% of the time. And it doesn't matter what we write for alias. Great. And so I guess the rejection probability here is 0, and the rejection probability here is 0.1. Does this sort of make sense, this alias table sampling? Seeing some nodding, some thumbs up. Great, 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 great. So that's, oh yes, One of the big bins to correspond to 2 of the other bins. If you wanted to, sample 0.1, 0.1, 0.8, were you asking, like, how do I construct that? If you wanted, well, I'm just going to demonstrate 0.1, 0.1, 0.8. If we did it this way, then, that's a nice 8. Then this would be 0.3. This would be 0.7. And now the probabilities all add up correctly.
No, I mean at the beginning there's a other 0.1 bin, then a 0.8 bin. So the 1/3 bin overlaps with 3 other bins, right?
We have discussion about whether it's possible to represent all probabilities. I have the constructive proof of that later in the talk.
Okay, I'll wait.
Cool. I'd love it if you interjected during that proof with detailed questions. Actually, let's go to that right now. So next up is a question of how. No, we're going to do one thing first. Performance optimization. Let's say you, let's not optimize to that quite yet. Drawing a random number between 1 and 3, anyone know how to do that off the top of their head? No hands. Anyone know how to draw a random number between 1 and 4? Yeah, we got some hands. The way to do it is you take a 64-bit random number generator, or random number, and you just take the first 2 bits. Very easy. So let's just do between 1 and 4. That seems faster. And we just put a 0 here. And that's a pretty major performance optimization. Just inflate to the next power of 2. So that's an optimization I use in my package. Oh, my timer is turning off. I need to know how long it's been. Oh, great. It's been 11 minutes. So the math is easier here because now we're working with quarters instead of thirds. And now we can talk about how to do a construction. So we start with, this is how much each result wants. And I'm going to switch back to 0.6 and 0.3 because I did that math previously. And this has division and addition and subtraction. I think it might have multiplication too. So that's like, that's a lot. Anyway, so we want, this one needs to give away everything. This one needs to give away some stuff. This one needs a little bit more. And this one needs a lot more. And so what we're going to do is we look at the ones that need to give stuff away and the ones that need to take stuff. And this is an O of n algorithm. It's pretty simple. Actually, very straightforward. You just take an arbitrary one that needs to give something away, and you put it to an arbitrary one that needs to take stuff. So I'll just start with this one, because it'll make the math easier. And I'm going to say, with a rejection probability of 1, or an acceptance probability of 0, we should distribute it to either 1 or 2. Let's do 1, because 1 comes before 2. Okay, so now this one is now in the wants to give stuff away camp. Because this one has a probability of 1/2 currently, because it's got its quarter and a quarter from here. And so it needs to give stuff away. And this stuff wants something, and this stuff wants to give something away. And by conservation of probability, we know that they're all going to add up eventually. And so now we can use this one or this one. Either way works. Let's do this one, because we were just talking about it. So it's got 0.25 locked in from here. That can't be given away. Once you're hit with, in the else branch of another bucket, that's a straight return. There's no redirection. So this thing needs 0.05 from its own original bucket, and 0.05 is 1/5 of 0.25. So we'll give an acceptance probability of 0.2, which means we're giving away 0.2 of probability. And we have to give that away to here, because this one doesn't want any more. So we'll give this to 2. Now this has 0.45 allocated towards it, 0.25 originally, plus 0.2. Yeah, plus 0.2 from bucket 1. So it needs a little bit more. This still needs to give something away. And 0.1 is 2/5 of 0.25, So this one will take 0.4 of its acceptance. And we're going with this one because it's the only one that wants to give more of its probability away. And that allocates to 2. And then I'm not going to do the math here. I'm just going to assert that because we're only transferring stuff around, it's got to add up if we keep everything for itself. Now, Jeff, do you have a question? Ah, Jeff says, I think I got it now. Great. Huzzah! So that's the construction algorithm. And there's like little details, but I'm not going to talk about the technical optimization of the construction algorithm because it's less fun to talk about. You can read the source code if you want, or talk to me after, or ask a question. So now let's talk about more optimizations of the sampling function. We've already made that a random number between 1 and a power of 2. There's another key departure from Walker's 1977 and other packages. I don't think any other Julia packages have done this. And that is, what it requires right now is a random integer that we're going to truncate and a random floating point number. And its accuracy is pretty good, but we still have like floating point numbers. Like floating point numbers, this algorithm was written for real numbers. And floating point numbers kind of can represent all the reals, but not quite. And I want it to be perfect, because of course, perfect is good. So let's get, next, I'm just gonna talk about this one. And this algorithm, just need to see the clock. We reuse the trailing bits. We take a single 64-bit integer, take the first few bits, or I guess it's take the first few bits and allocate those to determining which bucket it'll go to, and take the remainder of the bits and use that in the comparison to the acceptance probability. And when we do that, these acceptance probabilities now need to be unsigned integers. Instead of floating point numbers ranging from 0 to 1, they're unsigned integers ranging from 0 to the acceptance, to 2 to the 64 minus however many bits were being used to allocate, to pick the bucket. And accuracy is a great question to ask here. Like, can we get exactly what we're looking for if we've got unsigned integers in these values instead of real numbers? And the answer is mostly yes. You know how we were allocating probabilities earlier? Those probabilities, when we're allocating them, every time we transfer probabilities, we're transferring them in increments of 2 to the negative 120, 2 to the negative 64. Because if we think about, like, I use the term a pip to represent 2 to the probability of 2 to the negative 64. Each bucket is allocated, in this case, 2 to the 62 pips. And then the acceptance probability is between 0 and 2 to the 62 pips. And so then we're allocating, incrementing this by one bit, adding 1 to this unsigned integer, shifts 1 pip from one to another. And so we can produce any distribution over 2 to the 64 possible outcomes. And that is pretty much the best we can hope for. If we're taking one 64-bit integer, we can that's got 2 to the 64 possibilities, and we can discretely distribute them to any, according to any distribution. And so getting it precise, getting it efficient, that's most of what we're looking for in discrete random sampling. One thing you might be looking for is being able to mutate it in O of 1 time. Might give a talk on that next year, maybe, we'll see. Yeah, and some final, so a final note before we switch to questions, thank you, is this is this like pseudocode, this implementation that I've been talking about in the talk. This is the implementation, the actual package. Let me zoom out. Let me zoom out for a moment. Great. So only a few differences here. First of all, shift is computed based on the length of this vector. So in this case, shift would be 62. If there was more of them, then shift would be more, or less. And then some bit twiddling stuff. I found it faster to store the mask than to construct the mask based on 1 left shifted by shift minus 1 when constructing the mask to mask out before comparing to the acceptance probabilities. Storing acceptance probabilities and aliases together in one continuous chunk of memory, interleaved, so there's only one cache line lookup, is a small optimization. And then some funny business with mod int deleting an error case at inbounds with, it's got its own little proof. I proved it in the source code because, you know, have to use inbounds safely. Didn't include the proof here. And using this silly little construction to store, and this is just like fiddling around until the native code is most efficient. Storing as alias instead of the thing that it'll return, the difference between the thing it'll return and the current value, just results in fewer machine code instructions. So that's a little funny little details. And then there's the API, like plug it into Julia and such, and expose an API if you have your own random source of numbers, like you can just feed in the unsigned integer. And giving variable access to precision, so it could be int64, uint64, uint32, uint whatever. You know, all the little things that go into making a package that actually works. Yeah, so that's the gist of it. And now, let me go on to my next slide of my talk, which is questions. Any questions? Yes, please.
Hi, great talk. When you construct the alias table, considering you input like a general distribution, there must be some error. Is it possible that the construction function will return like a vector of the error on each bin, so you can make sure that it doesn't exceed some sort of tolerance that you have?
Yeah, so the way construction works, that's a great question, is first we normalize. So if you pass in a vector of unsigned integers and all those unsigned integers sum to 2 to the 64, then there will be 0 error anywhere. It's just perfect. And if you want me to normalize for you, I can't do that perfectly. If I can do it perfectly, I will do it perfectly. But if I can't, then there will be some slight error. And I worked really hard to minimize that. I think it's like half ULP stuff. I wrote this a while ago. I don't remember the exact details. And you can reconstruct the exact probability distribution of an alias table. We can see here, this display, that's displaying the exact probability distribution. So you can just compare that to your input, and that'll give you the error. Follow-up question from the same brother? Microphone troubles, making sure it's on. Check, check, check.
I meant the other way around. If you input a vector of reals, generalized reals, which might be some sort of weird Julia type number, then I would like a return value that shows the vector of differences of the alias table probabilities to my input, just for future verification if I add.
Yeah, absolutely. So let me demonstrate how that would be done. If we have weights, I'm not going to use custom in float types because I'm not going to precompile a package for that right now. And then I say, oh yeah, that's good. Oh, live coding. So if these are the weights, and then alias table equals this, and then I can say the probabilities Those are the probabilities. And then I can say, I'll divide those by 2 to the 64. And that's the new weights we're getting. And then I can say W2 minus W. And those are the errors, 2 to the negative 20-ish. And it turns out that the weights that we were asking for here are not divisible by, or they don't divide evenly into 2 to the 64. So this is, we gotta have some weight error. And 2 to the negative 20 is like, I don't know, what's that? 10 to the negative 20, yes. So it's off by, one of them's off by slightly more than 1 pip, the other are off by slightly less than 1 pip in the opposite direction. So that's, I'd say, the best we can do. That notably, and this is really cool, that is more accurate than float 64. And I use only float 64 and such in the input. So I don't remember what I was doing, but it must have been clever. Yeah, I compute the sum and then I divide and I convert to uint 64. So I'm not going to float 64. And if you give a float 64 input, okay, yeah, you see, float 64 input, I am losing a couple bits at the end. Oh well. Any other questions?
Okay, so yeah, very, very cool. So thank you for introducing, so I never encountered this idea by Walker before, very, very cool. The way that you demoed it up at the board here, you gave the weight to the very first bucket in need rather than a bucket most in need. I totally agree that this is going to be ON for the construction of this and then ON for the sampling. Is there any potential, could you ever be better off giving to a bucket more in need first so that you'll have fewer overflowing and then needing to flow some more weight back out like happened in this example?
Yeah, that's a very interesting question. Yes, it is possible to make a clever constructor that reduces or minimizes the amount of overflowing. With actual hardware on sampling, the sampling runtime is not affected by the amount of overflow because we're loading the alias anyway, and it's not, this whole sampling function is branchless, and so it doesn't actually save anything. However, it is a great intellectual question, and it is doable, and it's very hard, and I don't do it. And it reduces construction performance. But yeah, that is a clever thing to do. From the audience, it might be a bin packing problem. It's NP complete or something. Yeah, I think it's probably NP complete to minimize, but I don't actually know. I don't remember the specifics. I just remember thinking it was probably not worth it for my use case.
Wonderful. Well, we have time for one more very quick question. Otherwise, seeing no other hands, let's have a round of applause and we'll transition to the next speaker. All right, next up we have Ochibobo Warren, who's going to tell us about ortools.jl, bringing Google's optimization power to Julia. So Ochibobo, please take it away.
Thanks a lot, man. Hey, I'm going to be talking about the ortools.jl package, which is like a new package that tries to expose Google solvers to Julia. But a bit about me, I'm joining you guys all the way from Kenya. That's in East Africa. It's my first time in JuliaCon, my first time giving a talk. I'm really humbled to be here. Currently, I've really learned a lot. I like the pursuit of knowledge, especially with respect to science and computing. Currently, I work as a software engineer in Google, in the Nairobi office also in Kenya. I work in the Android team primarily. So what I'm presenting here served as we have this concept of like 20% projects, which is what you get to work on when you're not working on what you are hired on. And given that I'm a Julia enthusiast, this seemed like the thing to go. So I'll just get started. So ortools.jl in general is basically a layer, think of it as a glue, on top of Google's solvers that tries to expose the interface of Google solvers to like the Julia community. And then that glue also glues another interface that's present in Julia known as MathOpt interface, so that now you can use, there's a package called Jump. You can use Jump to actually do your optimization work using Google solvers. It'll be very easy. So let's just get started. So the agenda, the steps I'm going to follow is, of course, I won't assume knowledge in mathematical optimization. So I'll start with a brief on that, then a brief on MathOpt. So MathOpt is like the interface that Google has on top of the set of solvers that it exposes. Then I'll talk about the bridge, which is like the primary, like the objective of the talk, which is the ortools.jl package, a simple coding example to show you like the effect of having Jump on top of like MathOpt and how the code is actually reduced. Then finally, use cases and applications, and I'll finish my talk with like an opportunity for Q&A. So my background is not in operations research, which is where, okay, from what I've seen, that's where like mathematical optimization is pretty much dominant. My background is in like computer science. So in computing, when you have a problem, what you do is you get the input, you try and design the algorithm yourself, after multiple iterations to try to get an output. What I've seen in OR, in operations research, is that people actually use this thing called solvers. So you get the same input, you define your problem in form of like a model, meaning you have to have like some knowledge with respect to that, feed it into a tool called a solver, and then you get an output, which is kind of amazing because then you get to have a tool that solves not just one problem, so what an algorithm will do, but a class of problems. So math optimization is the science, think of it, it's just a science of making the best decision possible using like while respecting like a certain set of constraints or limitations that have been imposed to you, either physical limitations or real world limitations. The world has limits. So the goal of any mathematical optimization thing is to probably find the best solution to whichever problem you're trying to resolve, or even finding a solution if the problem is to deal with feasibility. The choices you make are going to be represented as variables, and then the limitations that are imposed on your problem are known as constraints. So the core things when you are working with solvers, in a general sense, you'll have to obviously define your decision variables, the thing that you want to make choices on, the constraints that you are facing, like the limitations that you have, and then finally the objective function. Like, are you trying to minimize something, maximize something, something of that sort, or are you just trying to find a feasible solution? So these three things primarily make what we call like a model. So a slight thing about how I ended up in MathOpt. So how I ended up in optimization. Initially, I used to work for like a logistics startup that's based in Kenya. When we were doing a bit of research with respect to how we can solve some of our problems, I came across the idea of like solvers and stuff. So that was about 2 years ago. I tried to like write my own constraint optimization solver by implementing a paper called MiniCP. It's actually free online. The goal there was to just do it for pedagogical purposes, to learn how you can actually write these tools before starting to like use the already existing tools in the market. It's quite a learning experience, I have to tell you that. The package is actually online. It's not registered. It's not part of Julia registry, but it's on my GitHub. I think with a couple of stars. I've tried to like document things on the README. It's kind of a huge one. Yeah, so that's more like it. Then I joined Google. Google has a set of solvers, a couple of them, some that they own, some that they do not own. but they want to expose and use one within Google and also expose the general audience. So Google has this thing called MathOpt. So MathOpt is just an interface that Google has defined that acts like a layer on top of a set of solvers that help you to solve or define and solve your problem in a way that is solver independent. What do I mean? So they're existing in the context of solvers. There are like multiple solvers that do exist. So what MathOpt does is it allows you to define your model independent of knowing which solver you're going to use. And then eventually you can just feed that model into different solvers. So how you define your model is independent from how it's independent from the solver that you'll use. But eventually there's kind of a guarantee, a contractual guarantee, that if the solver is being exposed through MathOpt, then you'll probably have a solution, or at least you can actually run it against the solver. These are the set of solvers that the current MathOpt implementation exposes. You'll notice that there are three that are predominantly starred. That's the CPSAT solver, there's the GLOB solver, and the PDLP solver. So these three are like Google-owned. The others like Gurobi, Skip, GLPK, HIGHS, or HIGHS, these are solvers offered by other, let me call them organizations. Some are commercial, some are open source, but they still get a space of being exposed through like the MathOpt interface. So let's just go to the next slide. Julia, as of today, there wasn't a way of accessing Google solvers through a Julia interface. Of course, Google has this tool called OR Tools. We won't assume you guys are familiar with it, but OR Tools currently offers support for Java, C++, and I think Python. And that meant that if you were accessing the solvers exposed from Google, you could only do that using those set of languages. If you want to do it via Julia, you'd have to find a way to either write a wrapper on top of the existing language or something of that sort, just tweaking things on their own. So the diagram at the bottom exposes the architecture of OR Tools. So the top package is the OR Tools layer. What that does is, okay, let me start with the bottom two. So the first one is OR Tools Generated. So OR Tools Generated contains a set of, a set of structures that map to the protos that are exposed through MathOpt. So the OR Tools Generated, these are Julia structures that are generated from the proto files in MathOpt. For those who don't know proto is just it's a data format that's used for serialization and communication over a network, something of that sort. They're very, very predominant in Google. That's what's predominantly used. So what we did is we got the set of protos in MathOpt, then used protobuf, which is a package used in Julia, and exposed the protos in Julia structs. So Julia structs that map to the protos. And that also comes with a set of functions to correctly serialize and deserialize any proto message that you send. And OR Tools, the JLL, that consists of C functions that call into the underlying C++ functions. Most of these solvers are actually implemented in C++. So once you have your OR tools, once you have your proto file, you feed them to the solvers that are in C++. So we needed a wrapper on top of that. So we have the OR tools, like the JLL wrapper on top of it that we feed the proto into. Then the OR tools.jl just acts as a glue in this way. One, it acts as a glue on top of the OR tools generated files, these are the set of protos, as a glue on top of the JLL, which are the C functions that we call using CCall. Then it's also a glue on top of the MathOpt interface. MathOpt interface is an interface or a package that's defined in Julia that tries to expose a set of functions or APIs that if you implement them, you get a guarantee that your solver will actually be accessible through JUMP eventually. So this is just a basic example that I wanted to show of how you can use ortools.jl in its pure form. So you're maximizing a profit from producing two products, X and Y. Product X gives you $10 per unit, Y gives you $15 per unit. Then you have a set of constraints where you have 100 available hours in labor, where product X takes 5 hours per unit, Y takes 10 hours per unit. And the materials, you have 120 unit materials, where product X takes 8 units and Y takes 6 units. So how will we do that in oracles.jl in its pure form? So, okay, this is just like the LaTeX representation. Try and condense all those words into just a simple representation that makes it a little bit clearer for like guys to understand. So the first thing you do is you import the OR tools. You initialize your model using the OR tools. It's called an optimizer, OR tools.optimizer. You define your variables. These are X and Y and stuff. The next thing is you define your constraints. We had labor constraints and cost constraints. We also had constraints to deal with both variables. You'll have values greater than 0. That's there by default in MathOpt, but then I didn't want to assume anything, so I just had to define it there. Then finally, you define your objective function. We're trying to like maximize our profits here. So you define your objective function in this case. You can actually print out the model, and then you also call like optimizing the model, and then when you print, you'll get like your solver results and stuff. So as you can see, for such a small problem, we've ended up defining like a lot of things. Like this is a lot of code for such a small problem. But the thing is, when we actually interfaced with MathOpt interface in Julia, we got exposed, or at least we got to satisfy the conditions that are probably needed to work with jump. So jump is like a common Julia package that you'll find being used mostly in like the optimization, or in mathematical optimization scenarios. So jump is just an interface in a certain sense, but it greatly reduces the code that one has to write. So from those 3, 4 files that we had, the same model can be defined using jump. You can see that the variable declaration becomes very small. The constraint definition becomes very short. The objective definition becomes very short. And I'm using just crude terms here. And this is such a basic example. You call the optimizer on the same thing. Then you can also obviously print your results and whatever. So the good thing now that you have OR tools, it means that in the same way you would access solvers using like jump, how you'd access Gurobi and whatnot, it's the same way now you can actually have access to like Google-defined solvers. The optimizer, the OR tools optimizer that's present here, that's present there, allows you to define parameters with respect to which solver you're going for. So are you going for like the PDLP or CPSAT, or are you going for GLOB or whichever? Yeah. Then a few examples of how Google uses solvers. I provided links so that it might be easier for like guys to just go through them instead of me explaining them. So you have like the workforce scheduling API, you have a shipping network design API. You're not just scoped to this. When you go to the OR tools site, every example that's present there in like other languages can also be accomplished using like the Julia language now that OR tools is present. Then how Google uses the solvers, mostly it's for resource planning, resource and capacity planning in data centers. Then real-world applications, this is in a broad sense. You're not just scoped to this. You can use them in logistics, as I told you, that's where I started off, in scheduling, in finance, in energy, and in many more, depending on how you'll actually define your problem and whether the tool actually fits the bill. Then, a bit of the hurdles that we faced while we were working on this. So, when I started off, I didn't mention who I also worked with on this. His name is Steve Out. He works at Google, but he works in the operations research team, so he's more aware of the solvers than I am. But it was more of a collaborative effort at the end of the day. So one of the hurdles that we faced was the MathOpt interface is it's a large interface. Like there are a lot of things that you have to implement, that you'd want to implement in order to like satisfy, in order to like expose everything that's present in your solver. And it also comes with like a set of tests. So sometimes you implement things, you run the test, your tests fail. Sometimes the tests pass. So it was kind of like a back and forth, but the interface is quite large. Though it was both an enjoyable and hurtful experience. Then the second was the protobuf .jl package. Protobuf currently, when you generate like Julia structures from the proto data format, it assumes immutability, or the structs that are generated are actually immutable. So it's just struct, then the struct's name. You don't have the option of generating mutable structs. So when we face this hurdle, because we have structures that actually get updated as you are defining your model, for example, the model itself is a structure that gets updated as you define it. So I tried to like open up, to reach out to the maintainer. It wasn't kind of easy to even find who was the current maintainer of the package. Then eventually, after getting to the by the time we were getting to the maintainer, time had already gone. So what we had done is we had written like mutable wrappers on top of our existing structures, which just made the process longer. But now I have like a PR at least that will try and add like the ability to specify that you need mutable structs to be generated from a particular set of properties. Then the JLL wrapper, I remember this took a long time. I didn't particularly work on it. This was work that's primarily done by T-Bout. Yeah, that's all I can write there, because it took a long time, so I'm sure there were kind of hurdles that he faced. So what are the next plans with ortools.jl? Cool. So currently the one solver that we support fully is like the glob solver for linear programming problems. But we need to complete the support for PDLP, offer public documentation with examples, of course complete the support for like the CPSAT solver for like integer problems and constraint problems. Then there's this thing where we want to add like support for remote solver calls. So when you install the package currently, you'll have the package running and like solving the things on your machine. So we'd want to allow you to, yes, call the package locally, and then, yeah? Oh, okay. Yeah, so we'd want you to be able to like have Google servers do the solving for you. So if your model is quite huge and maybe it'll consume a lot of machine resources, you can just send it there. Just post your like model to Google servers online, then they'll do the solving for you. Currently, we don't have support for quadratic optimization problems. We'd want to add support for multiple objectives. And our goal is to have like the first major release in September 2025. So currently, we do have like the JL package. I think it was merged today, ortools.jl. But I define that as like the alpha version. So on September 2025, because we also want the package to be ready, one for the JuliaCon that'll be in Europe and the other one, and for Jump, like the Jump DevCon that will be in New Zealand in November. We want the package to be ready and also battle tested. So expect the first initial, like major initial release by September 2000, of course this year, not 2025. Yeah, and that's all about it, man. That's all about me. The package focused more, I focused more on the layer, not on the solvers, because I never wrote the solvers, not really fully aware of how they work. But if you have like concerns about them, you can reach out to me and I can obviously try and like find someone who will really help you out. So thanks, that's the end of my talk. Cool.
Well, thank you for the talk. I think it was very interesting to see this, being familiar with Jump and everything. And I was curious about maybe Google's vision or your vision, your team's vision on how this integration helps you, given that some of the solvers that are available through OR tools were already previously available through Jump. So you see any performance gains in this sense? How does that compare? And also, how you see this being used in Jump, especially the solvers that are related to constraint programming, because this is something very recent in Jump, so I want to see how you use them.
Cool. Awesome. So the first question was with respect to the gains that we have by having this. Cool. Yeah. When you look at and you're right about other solvers already having like existing packages in Julia, like Skip has its package, Highs has their package and stuff. So yeah, these solvers will also be offered through like the OR tools interface, because they're also offered using Google, through Google. But then the three that we are predominantly focusing on were like CPSAT, GLOP, and PDLP. I've had a lot of interest with respect to like the PDLP solver, especially if you have like a large, if your model ends up being large. Of course, the trade-off there will probably be in terms of maybe the model accuracy, something of that sort, but you will probably get a solution with respect to it. So the gain here will be, one, we are exposing our solvers to the Julia community, and the Julia community has like a very, very solid presence when it comes to mathematical optimization, especially through Jump. The other gain is, okay, this is just my perspective, probably looking forward to PRs. So when it's open source and stuff, and you have this engagement from people who have experience in a particular field, but in a way that's not unique to Google, at least incorporating the ideas into improving the tool will not only improve the tool for Julia, but also improve Google's tool in general. Yeah, have I answered your first question? What was the second one, kindly?
The second one was more about CPSAT, GLOP, and PDLP, and your experience with the new jump interface for constraint programming. Because Julia, in Jump, you usually do linear programming, quadratic, and conic was very well established, but the interface for like set problems is quite new.
Oh,
so
okay.
I wanted to see
Cool.
what's your experience with that?
Awesome. I didn't know there's a new Jump interface, to be honest. So, okay, because currently the implementation we've only done completely for the linear programming bit, which is GLOP. I think that's why I haven't come across like such things. But the good thing with like the MathOpt interface is we found it to be very extensible. So if there's if there's missing support for particular features, even in our current implementation, we just extend some abstract thing. Of course, we try as best as possible to offer a clear definition with respect to, hey, this, like a clear documentation, this is how we use this structure and whatnot. So I think we'll be able to, especially for the CP-SAT things. I know there are things that are unique, like in the SAT world, for instance, like constraints like all different and something and things in that line. I didn't know they were new. I thought they were there initially, so I'll probably have to look into the new bit. I wasn't aware of that, but I think we'll make do with it. Yeah. Cool. Thanks, man. Thanks. Yeah.
Thank you very much. Thank you very much for your talk.
Awesome, man.
And I also couldn't imagine giving this talk with the amount of jet lag that you must have, having traveled all the way that you've traveled here. So I've got a couple things I'm curious about, but let me ask about one of these. So all of these solvers, some of which were developed by Google that you have highlighted there, for folks at Google who make use of these things for doing OR work of various kinds, you are a Julia enthusiast in a jungle where there are probably some other Julia enthusiasts and probably some who are not.
Correct.
What kinds of interfaces do a lot of your colleagues use who are not Julia enthusiasts to access all of this stuff? And have you had any conversations about trying to convert people to Julia? I'm kind of curious about the range of practices that you see to make use of these tools right now at Google.
Okay, in Julia or the tools in general?
The tools in general.
Cool. So what I've seen, okay, I don't work in the operations research team, so I'm speaking from like a external perspective. Yeah. So what I've seen is there've been some efforts, especially with guys from the OR team, to try and reach out to members of other teams, like in Waymo, for example, to try and get them to use like the solvers. The predominant interface, of course, we try to define our APIs using the proto, which kind of makes us language independent in a certain sense, apart from when you come to implementation details. However, C++ is quite dominant there, and Python is actually quite dominant. So where does that leave Julia? We have these like small, I'd call it small because it is small, but it's growing, like a small Julia group that tries to work on Julia stuff within the scope of Google. Let's just try and either add wrappers onto them to try and make Julia more active. I'd say it's kind of growing, but we still have some way to go in order to get like a critical mass such that Julia might be probably considered as one of the go-to languages for certain use cases or certain problems within Google. Yeah, I think the buck stops with us. If you write Julia, try and push for it, something of that sort within the organization. Yeah, but at least I'd say we've kind of progressed very well, especially with the OR tools. The OR team is quite receptive to Julia, given their knowledge of how impactful like Julia users are to like mathematical optimization. So they are very receptive to that. That I can tell you. Yeah.
Gotcha. Thank you.
Cool.
We've got time for another question, or perhaps two, if we've got. I've got a very quick follow-up question to that, which is, no, it's far less serious than the last question, but in some sense, a lot more serious. So I never thought before about the Julia color scheme versus the Google color scheme, that you've of course got the red, the green, and the blue in common, and then differing in the purple versus the yellow.
Yeah.
How close are the Google red, green, and blue to the Julia red, green, and blue? Have you ever given this any thought? I never thought about this until your title slide, where both logos were up side by side.
Really? I didn't even notice that, man. Okay.
Yeah, they're quite similar. So in terms of the future of Julia at Google, or Google tools for Julia, there's some thought about what the closest matched color palette would be. Yeah.
I don't have any thoughts on that, but maybe I should think about it and get back to you.
More of a comment than a question, I suppose.
Pardon?
more of a comment than a question, I suppose.
Okay. Yeah. Now that I look at it,
they're awfully similar.
Yeah, with a slight difference in the amber, but you're right, man. In the purple, yeah. Cool, yeah.
Thank you. We've got time for another question. We've got one in the audience. All right, well, seeing none others, let's have another round of applause for Ochibobo. Thank you very much.
Thanks a lot, man.
And we have time to transition to our next speaker. It started in about 45 seconds, right at 2:30. All right, next up we have Yuri Nushdin from ASML, who's going to tell us about Julia in C world, fast, safe, and seamless. So Yuri, please take it away.
Yes, thank you. Indeed, we in ASML, we're really looking how to integrate Julia on our machines. We actually have a much deeper talk about all this tomorrow at main stage at 11. But in this part, I will just focus on one particular aspect of this big trouble, is how to actually coexist with the existing algorithms. ASML produces a very complex machine. We have a lot of interfaces, we have a lot of interfaces. They are made with C, C++, Python, not with Julia. And now we start introducing Julia, and it's just a few, but we cannot just make it as a model that exists in its own space. It actually needs to communicate to the machine back and forth. Hence, we need to call it. We need to call C, and we need to be called from C. Of course, this is not the first time we tackle with this problem. Other people had this kind of challenge. But in ASML, we also have an additional challenge that we use internally, our internal DSL to describe those interfaces. And it's not really like C++ oriented, so CX6 wrap was not really a feasible option. It's more like C-based, and I will explain you what it is a little bit later. But first, what is actually available? So assuming that we need to talk to C, what's available? Well, great documentation from the Julia. It really tells you how to integrate it, but it's intended for the C developers. It's the same problems every time, right? If you want to know how to manage memory manually, if you want to know what is the pointer and how the segfault looks, that's your choice. We said that, okay, this is very nice. This gives you reasonable performance. This gives you actually quite good performance. But if we want to make it available not only for our C engineers, but also for our engineers who just work with the models, they don't need to learn all this complex stuff, which is kind of available as well, but it have a significant performance cost. So everything in this documentation is very unsafe, but if you just can afford to copy all the data inside of Julia, then it's not a problem. In our case, it is a problem because we process a lot of data and it would be really slow. So what do we actually... Okay. Something went wrong. Is it? Anyway, we want to make our engineers able to write regular Julia code. Some example you can see on the left. It almost seems familiar, right? There is one special macro. This is about our internal DSL description, but everything else looks like a code that you can write. But it actually works with the interfaces and the structure definitions from this internal DSL, but it does it in very transparent way. Why? Internally, we pass the pointer here. This is what happens under the curtain. So people who just work with the models or with the algorithms, they don't see it, but internally it's past the pointer, it's wrapped in one wrapper, it's wrapped in a memory safety wrapper, and it's also probably went through the interface adapter, and you don't see it, you just interact with it. And in this talk, I will just talk you through how we're making those wrappers. So if you want to have something similar in your use case, you can kind of use it as a reference how it can be done. So let's start about our internal DSL. It's very simple. It was invented somewhere in the 90s. So it's really C-oriented. It supports structs. It supports vectors as a dynamic entity. It supports arrays as a static entity. It supports strings. It supports primitive values. And it actually can allow you to define interfaces and call them back and forth, right? So you can implement your own interface, and you can be called. It have a bindings to C, C++, Python, and that's what we introduced, Julia. And it also hides a lot of, it's a kind of great tool for us because it hides the remote connections, it hides IPC, it's very nice. And we have to use it. So what does it really offers us? Okay, first thing first, of course, primitive types. In Julia, it's very easy because primitive types are also first-class citizens for Julia. Julia really understands them. There is one specific case of enum, which is in binary is indeed represented as integer, but in Julia it has a special meaning. That's the only thing you need to care of. And one nice convenience for us is that all primitive types that we use are inherited from the number. So part of the code can be really simplified by not mentioning all of them together. Vectors. Well, vector is a simple thing. In our case, it just contains the pointer to the, this is what I wanted to like represent. It contains the size and the pointer to the data. And in our case, well, this is how it works. If we want to work with them, we have to define certain methods, and we use the methods that Julia defines for the abstract arrays to work with the abstract arrays. So we overload them. So if you start using the vectors directly, you don't see that it's wrapped in something, right? Which allows you to say, okay, if this code can work with something that looks like a vector, it keeps working with something that looks like a vector. I highlighted here propagating bounds. You will see it many times on the slides. And it's a very nice mechanism which allows you to play with the safety checks, right? Because in principle, working with pointers is unsafe. The pointers can change, the pointers can get out of scope and all this kind of stuff. So there is a lot of mechanism built in for pointer safety. But internally, when you already know that the pointer is safe, you can actually opt out. And Julia, with this propagating bounds, really gives you a very nice tool to semantically correct, to do this opt-out thing. I know it's fine. It's guaranteed. It's risky when you, as a user, claim this because maybe you checked it wrong. But as a library internals, it's really useful to switch it off at a certain moment. Structures is, in principle, same idea. We have a pointer. Well, we know how the pointer is structurized. It has fields, etc. You need to take care of memory alignment. And we have internally, we have a kind of big problem with that. We have several memory alignment schematics for some reason. So, but in general, if you're a C developer, you're familiar with memory alignment and how this done. You just work with the pointers, and the nice abstraction that we found is that our structures, they don't return back. For example, here we have a get property, right? So get property is what is called when you say a dot something. Okay, in this case, you can actually generate this kind of code. This is generated by the macro. And you can see that it just returns a pointer value. This is the nice way how we found how we can actually express back to the system that's the value. You need to take care of it. And because we do it in such a way, and it's also inline, it's static call graph compatible. So we as soon as we introduced inlines here, it became static call graph compatible. It's very nice for us because we use this feature. This is how we deal with the structure. So this is first layer. Pointers have the data access wrappers. Data access wrappers just explains to the language what we can do with this, right? Because structures have fields, vectors have elements, primitives doesn't have anything. They would be just the pointers. Next layer. Next layer is memory safety. As I said, this is returning still pointer. It's still raw pointer. Nobody guarantees that it's a valid pointer. You can think about all kinds of use cases. For example, you passed the value inside of the function, but developer decided to put this value in a global. Well, you don't know at which moment this pointer becomes invalid. So we need some invalidation mechanism. And we need a safety around it. The schema that we found to deal with it rotates around one interesting concept where we create this just a Boolean, but we purposely make it mutable, which means it always sits on a heap. And then we have this owned mutable wrapper, which takes care not only about releasing the pointer, if it can be released, but it also always carries this safety flag. And the idea is that as soon as safety flag is raised, it's safe. If it's lowered, it's unsafe, and you need to go through the acquisition procedure, right? Of course, for the root object, the one which was given to you directly, you can kind of know it's the pointer that I get when the function was called. It's still valid while I'm in this function. But for the sub-elements, it's not guaranteed, because you need to think about use cases like array got resized, vector got resized, and it was reallocated somewhere else. In this case, we track these sub-elements with index mutable wrapper and field mutable wrapper, and you can see that like field mutable wrapper is x dot something, and this is your field, and x square bracket something is your index. So we actually know. Yes? It's not really a shared pointer. It's just tracking the pointers and where they originated from. And I will explain how it works right now. So this is how it works. Let's say we get a structure which have a vector, which have some sub-elements, whatever. So far, it is great. It's fine. But somebody decided that this vector should be resized. So we created a new element in the memory. We don't know, actually. We don't make an assumption that it is safe. We just mark, OK, it's unsafe now. All of these wrappers, which points to the particular elements in this tree, now pointing to the safety, which is lowered. And by the way, you cannot raise the safety. It's just like restricted. We overload the function. So what do we do now? When we access to the certain field, the field says, OK, I'm pointing to the lowered safety. I need to restore it back. And then it goes through the parents, right? Because all of them have parents. Eventually, it goes to something which says, oh, I own the pointer. I know it's safe. In this case, it goes directly to onMutable. It says, OK, I'm safe. Here's your new safety element. I will attach it to myself. And you can attach it to yourself as well, right? So now in a heap, we have safety which says I'm unsafe, and the safety which says, well, now I am safe. But only this element is pointing to it, right? What if we access this element? Well, say, I realize that you don't see the mouse pointer. I'm sorry for that. Can you see it now? OK. Something went wrong. Can you see it now? Yes. Well, sorry for that. I was showing everything on my screen. That's not good. Right, so that was the element that we reacquired, right? Those are not reacquired yet. Let's say we access here. Well, this one is saying, OK, I need to reacquire. I'll go to the previous one. Oh, this was also unsafe. It doesn't know if it's the same pointer or not. It will reacquire itself, and it will go to onMutable. And it will find, and onMutable at this moment will tell, that's my root pointer, maybe it's a new one. And you know that this is certain offset, right? It's indexed mutable. It keeps inside, I'm element number 2, so it can just recompute what's the new position in memory. And at this moment, it says, OK, I'm reacquired. I will point to this new safety. And the same here, if it's a field, it says, OK, I'm field X, and I'm required as well. So all of them are pointing to the safety. They are happy to report back that you can use us. This one is just left for GC, right? If they will fail reacquire, then you will have a runtime exception. And that's how you know, OK, maybe this element was removed from vector completely. Right? This is the safety mechanism that we have. Let's go further. Further is interface wrappers. Why? Because we want to have higher level, higher order function structures, right? We do a lot of math in essence, and as I said, the type system of our DSL is very limiting, so we build something on top of it, right? And the matrix, in essence, is just like a size of the matrix plus data, which is represented in a vector format. And we support, like, at this moment, we just focus on like matrices, tensors, and sparse matrices, which is very nice. The downside of this approach, as I said, we overloaded a lot of base functions to make and feel those memory safety pointers behave like vectors and behave like structures, which actually solves the problem of writing the code, which works with it. It doesn't solve the problem of type system. I think it's my mistake that I did it in such a way that you can work with them as vectors, which sounds like why? It's actually convenient. Would be much more convenient if they would be inherited from abstract array, for example, for the vector. I was really lost in a type system then. I will redo this. I will not advise you to do this. Just make interface wrappers for everything. It doesn't really cost that much. I remeasured it. Julia really able to optimize all this out. It like really removes all these 3 layers of abstraction. It just says, okay, this is how we work with the pointers. That's it. But it saves a lot of hassle with interaction with the code, because now your code can be more strictly typed. You can say, well, this works with abstract array. You don't need to make a wrapper around it. But I didn't do it. And then I had to make a wrapper around it. So now developers are forced, if they throw it in their code, they can just say, okay, this is any, and Julia will figure it out. But if they send it to some predefined function, they wrap it in a DD array view, which hides internally array, and it has the safety mechanism, and internally just knows where it's acquired. Nice. For me, it was at this moment very convenient to say, well, the matrices cannot be resized. This is fine. This really simplifies both wrapper and life of developers, I believe, as well. Same here for sparse matrix, and if you can see here for a DD array, unfortunately you have to define a lot of, it's a trivial code everywhere. I didn't print it because it's obviously how to measure length of this structure, but you have to define all of them. You can read documentation to find which interfaces to define, or you can just take a screenshot. For sparse matrix, I'm happily surprised how less you need to define. You just do this and it works. The only trick was insert bank. You can look inside sparse arrays to see why. So you can omit it, but then the performance will not be that great and it will not be static compilable. Yeah, and in general, this is my mistake. This is like how I did like resize. Well, resize is not existing in Julia, but all of these things, I made it so you can transparently work with it, and it will pretend that it's a structure, or it will pretend that it's an array, which is nice, but again, I don't advise you to do it like that. Just make wrappers around everything. What's about performance? Because in the end, this was done for 2 purposes. One, writing the Julia code. As I showed you on the first slide, it looks exactly like a Julia code, so no problem with that. But what's about performance? Does it really solve it? I took one, I simplified one of the examples. Of course, we do the modeling, but in essence, this model was really like, we sent something which looks like a gigabyte of data inside of the model, we update it a bit, and then we take it back, and then back and forth. Back and forth was the biggest problem, because you not only copy it inside of Julia memory, you also copied it out. That was a requirement of the system, but yeah, if we can save half a second, we could. But we could not. So here you can see just back and forth, very safe, very easy, 1 second, run in 1 second. Ideal way is, well, you don't do this. You just have Julia code for the whole system, very nice, super happy. This is the measurement, this is like 10 microseconds, very nice. And you can see that overhead exists, like the third one is pointer-based access. So it actually ensures the safety all the time. It makes sure that it's fine, but actually the overhead is not that high. And if you say, this is just for subarray of size of 100, which is actually not usually the case. It's usually around 1,000, and then it's, of course, then it's kind of on par. You don't see big delays because of that, which actually allows us to work with the data which is located somewhere in our system, and back and forth. And I'm not showing on this presentation, but it's not only that we implement a model which is called by the system, but this model actually calls the system as well. And because it's a symmetric interface, then this data goes back and forth seamlessly, and the performance impact is really, really low, and Julia gives you all abilities to do that. So that's the memory safety mechanism. I saw that I will spend much more time on explaining this. I didn't went to like function pointers, etc., but they are really, really specific for how it's internally organized on us. And I would admit, I would like to make this open source, but for obvious reasons, like it's an internal DSL language, I cannot really make it completely open source. And I struggle to find what's actually useful. I think like safety mechanism probably useful, maybe structs are useful, how we deal with our internal definition of vectors, probably not useful at all. So if you are sitting and thinking like, okay, they actually did it really nice and it seems to be working and we may need to have similar approach, just reach me out and we will find out what we can share, what we cannot share, and how can we help each other. Because I think in the end, it would be nice to publish part of it, but that's my small request to you. If you see a value from it, just let us know, and we'll figure out something. And I invite you to our talk tomorrow, where we will talk about JuliaC being used to actually compile all this code plus the models and deploy it on a machine, and how we struggle with it and how it was a success for us. And if you're interested, also talk to us more about our use case of deploying Julia algorithms on a machine in a close to like stiff real-time environment. We have a lunch at 12 tomorrow in one of the rooms, so please join as well. We would like to hear your stories. We also would like to hear how you tackle the same problems. We're really curious to know what's going on in the industry in the same way. And yeah, that's the end of my talk. I'm waiting for your questions.
One question, I guess, that came up to my mind in the safety mechanism, and the answer might just be, I don't care about that, is thread safety, right? So I know it's a difficult question. I mean, the answer might just be, yeah, we only have one thread running, so it doesn't matter. But like, is there a way you can do thread safety? You could say like, oh, all access have to be, like safety access have to be behind a lock or something like that.
We did not look into this because it's one of our limitations. This interface was really made, this DSL was really made before multi-threading became a thing. It's just non-reentrant, so we don't have a use case for that. I think it's possible to make something thread safe there, but it's also like intended for JuliaC, which is at this moment is also like not really there to have multi-threaded environments.
Yeah, I imagine it was something like that, so thank you.
So yeah, the short answer is like, this is not thread safety. No, it's unsafe, no.
Yeah, thanks for the talk. So you talked a bunch about this kind of pointer safety mechanism. So and I think one of the issues, let's say, is that you're working with raw C pointers, which kind of allow anything. So let's say you work with something where actually on the C side you have much stronger guarantees. So actually, maybe you're in C++, and maybe you have already some shared pointer or some kind of more safe pointer. Do you think that if you get more guarantees from the C side of things, that kind of erases most of the issues that you have in the interface?
No, it's actually intended to catch. Yeah, you can start defending it from the C side, but you still have the Julia side where you actually make interface which doesn't reveal that you do this, which means that on a Julia side it can go completely wrong, right? And because it still works like iterators in essence, right? It have all these problems which Julia doesn't have by not having iterators. You can save iterator, it's a variable. You can put it in a global, and then half an hour later, you can access it, and it would be pointing somewhere, unfortunately. And you need to catch this. So it's a really prevention mechanism that from Julia's side, you cannot have seg faults.
Okay. And maybe some
static analysis? Would that do you think that could resolve some of these issues, or would it be too challenging?
I think it's quite challenging indeed.
Thank you.
I'm kind of cheating because I know some of the things behind this. But I noticed that you don't talk about any of the words that we run into, any of the problems. Could you just quickly say where were the things where we got stuck, or actually you?
Well, I think I mentioned that the interface I'm not super happy with, but in essence, that's not that difficult. I mean, of course, you need to be really careful. Most of the problems I had was accidental seg faults because I did not really understood the ABI of our interfaces, which also appear to be fluid, but like, let's not talk about this. As soon as you do something right here, and as soon as you can write a C code which should do these operations, you can easily write the equivalent Julia code which will do it exactly in the same way.
And with trim? With Julia C?
Trim, yes. Trim, we had some problems with that. This is why I highlighted inline. For example, inlining, because this builds very deep structure. By default, Julia thinks this is too deep to analyze. By marking everything inline, you actually solve it, because then Julia is forced to really analyze it. And in essence, this is trimmable. This is type stable. Yeah, you just need to hint Julia what to do with that.
Great, thanks. Well, I remember that sometimes code was removed from these parts, but that was a different story.
Thank you.
All right, next up we have Stephen Whitaker from the Great Lakes Consulting Services, who's going to tell us about integrating Julia and MATLAB, subtitled Julia and MATLAB Can Coexist. Stephen, please take it away.
And thank you for the introduction. So I'm going to be talking about Julia MATLAB integration. I'll start by talking about why we might want to do this, why not just stick with MATLAB, or why not transition entirely to Julia. I'll talk about how to actually do the integration, and I'll walk through an example model. I'll show you the MATLAB code, show how it needs to be translated to Julia and then reintegrated back into the MATLAB workflow that we're working with. And I'll demonstrate some benchmark results from before and after doing the Julia MATLAB integration. So to begin, I do want to say that from our perspective, MATLAB is great software. It's used by businesses and people all over the world, and it has withstood the test of time. MATLAB has excellent tooling and documentation. It has been the go-to for scientific computing and engineering, and it is ubiquitous in modeling and simulation. So by a quick raise of hands, who here has written a model or a function in MATLAB? Okay, I think literally everyone. Me too. So engineers have had decades worth of MATLAB models and workflows, which is to say MATLAB isn't going anywhere. But is MATLAB the best option in all cases? Now there's this trade-off between speed and what I'll call reputation. So MATLAB has an incredibly good reputation. It has excellent tooling, it's robust, and it has a ton of other awesome features. It has gained a reputation for being reliable, and it is an established industry standard. Large companies may have hundreds of MATLAB models and thousands upon thousands of lines of MATLAB code. But that makes it not practical to switch all this MATLAB code entirely over to Julia all at once. However, there may be instances where MATLAB isn't the best choice to use. For example, if you have performance critical or large-scale models where speed is absolutely paramount, a language like Julia may be more suitable for those cases. So let's look at some concrete numbers. I pulled some benchmarks from the SciML Benchmarks website, and as an aside, for those of you who haven't heard about the SciML ecosystem, the Julia scientific machine learning ecosystem is incredible, so check it out if you haven't yet. So what these benchmarks do is it compares ODE solvers from various languages for various ODEs and just sees how fast do these ODE solvers compare. So for one example, we have a non-stiff problem. Here we're plotting how long it takes these ODE solvers to solve this non-stiff problem. The Julia solvers are in green, MATLAB in orange. And looking at this plot, we see that for this particular non-stiff problem, Julia is 10 to 1,000 times faster than MATLAB. Now, what about a stiff problem? A similar story for this particular stiff problem. Julia is 10 to 1,000 times faster than MATLAB. So now consider if your long simulations or parameter optimizations take hours or even days to run in MATLAB. You have to start asking yourself, is it worth using MATLAB when time is money? Does the reputation of MATLAB really outweigh the cost in time? So the key question is, how do we get Julia's speed, but without rewriting all of our MATLAB code in Julia? How can we get that speed without major disruption, without completely retooling everything? So another question, does anyone here, by the raise of hand, work with large MATLAB code bases? All right, a few of you. So, like I said, companies have had decades to amass tons of MATLAB code. And so if you're working at a company that has a large MATLAB code base, if you use MATLAB every day, your colleagues use MATLAB every day, and frankly, this code works, it runs, it gives the results that you need. I mean, these are all valid reasons for sticking with MATLAB. Oh, but the speed, Julia is fast. And some might say that Julia is the superior language. I mean, that's why we're here at JuliaCon, because we want to use Julia. So the good news is that there is a way to introduce Julia into your MATLAB workflows. And you can do this with minimal disruption. You'll want to start small, so pinpoint the particular pain point in the MATLAB workflow that you have and start targeting that area. You want to keep your existing MATLAB workflows intact. That way you help keep people on board with your project. But then most importantly, you also want to show meaningful performance wins, because that's ultimately what gets people's attention. So for the rest of my talk, I'm going to walk through the process of doing Julia MATLAB integration using an example model. So the example model that I'll use includes 50 equations and state variables, along with 37 model parameters. We'll also have discrete events and continuous events. For the discrete events, we're going to update one of the parameters at 4 specific time points along the simulation. An example of this in practice might be injecting a dose of medicine or modifying the thrust provided by a rocket. We'll also have a continuous event where we will modify a state variable when it reaches a certain value. Now, the classic example of this is when modeling the velocity of objects that collide with boundaries. For example, if you drop a ball, that ball is going to fall until it hits the ground, and when it hits the ground, it doesn't keep falling. There's an event that occurs that causes the ball to bounce. So that's the sort of thing that's captured by these continuous events. For our example, we'll look at 2 problems of interest. One is just simply solving the ODE one time. How long does it take to do that? But then in practice, we don't normally solve an ODE a single time and then call it quits. Normally, we're solving ODEs many, many times. So we're also going to look at doing a parameter sweep where we'll solve this example model ODE with about 200,000 different sets of model parameters, and then choose the one to use in production. To illustrate this model a bit more, here are 3 of the state variables plotted over time. The first plot is a state variable of interest, so this might represent the position of a mechanical part, or maybe it's the temperature of concrete or some other substance that we're modeling over time. The second plot illustrates the discrete events. So at these particular time points, we're changing one of the model parameters, and we see how that influences the time course for the state variable. And then the third plot illustrates the continuous events, where when this state variable reaches a value of -10 or -2, we negate its derivative, and we see how the time course is influenced as a result. So looking back at the first state variable, here I'm plotting it for 2 different sets of model parameters. The first set of model parameters results in these large oscillations, while the second set of model parameters has virtually no oscillations. So the first question is, how long did it take to solve this ODE one time so we can get this plot? Solving this ODE in MATLAB took about 20 milliseconds. Okay, so maybe that's not so bad. Now, going back to this plot, like I mentioned, this state variable might represent the position of a mechanical part. And so if we have these oscillations, we can imagine that those oscillations cause wear on this mechanical part. And as a result, we would love to use the second set of model parameters so that there's less wear on that part, which means we don't have to replace it as often, which saves our company money. The problem is we don't know what those parameters are beforehand. Okay, so what we'll do is we'll pick 200,000 different sets of parameter values. We'll solve the ODE with each of those sets of parameter values and choose the parameter set that minimizes the oscillations so that we don't have to replace this part so often. Now, if we do this parameter sweep in MATLAB, it takes about 5 hours to run on my laptop. Now, if you run this exactly one time, maybe that's not such a huge deal. But if this is part of continuous integration or testing, or if you do a parameter sweep for many different models and many different workflows, you can see how the time starts to add up quickly. So we want to see how Julia can fare in this situation. So what we're going to do is we're going to take our MATLAB parameter sweep, and we're going to need to translate that into Julia, but then reconnect it into our MATLAB workflow. So the first thing to mention when converting from MATLAB to Julia is the syntax. So MATLAB and Julia have a very similar syntax. MATLAB was the language that I used primarily before I started using Julia. And when I started learning Julia, it almost didn't feel like I was learning a new language. That's how similar the syntax was to me. In terms of the dynamics, Julia is designed for performance. So in MATLAB, every time the ODE solver calls out to your dynamics function, it has to allocate new memory in order to store the results of the computed state derivatives. Whereas in Julia, you can allocate that memory up front, and then every time the ODE solver calls out to your dynamics function, it can reuse that memory, which boosts performance. I found that in Julia, working with events and callbacks was more intuitive and easier to do. For this particular example, I was able to define them in fewer lines of code in Julia. Julia provides for better code organization, and Julia also provides many pre-built callbacks that you can use out of the box. So looking more into events and callbacks, so here's some example code in MATLAB and in Julia for defining events and callbacks. So in MATLAB, we have one file for the events and then a separate file for all the callbacks. Whereas in Julia, we can define the events and the corresponding callbacks together in the same file, which allows for better code organization. Additionally, in MATLAB, we have a single function that defines all of the events, and then we have a single function that defines all of the callbacks. In Julia, we can be more modular. We can define a single function per event, a single function per callback. And then finally, in MATLAB, there's more bookkeeping that we have to do on our own. So we have to keep track of indexes of the events. We have to manually check if events occur, manually call the correct callbacks if those events occur. Whereas Julia takes care of all of that for us. In Julia, all we have to do is explicitly pair an event with its callback, and then Julia takes care of the rest. Julia will check if the event occurs. It will then call the correct callback that you assigned it, and we don't have to worry about that ourselves. So again, I found that working with events and callbacks in Julia was more intuitive and easier to do. Now, another consideration when adopting a new software is how much learning do you have to do in order to get up and running with it. So I already mentioned the syntax. Julia's syntax is similar to MATLAB, and so that isn't much of a barrier to entry. Then there's also what packages are available and how quickly can I learn those packages. So for this particular example, I only needed to use 2 Julia packages to get it up and running. So I used diffeq callbacks for the events and callbacks, and ordinary diffeq for setting up and solving the ODE. And then perhaps more importantly is part of learning a package is going through its documentation and learning how to use the package from the documentation. So how good is the documentation? So particularly for the SciML ecosystem, but also other ecosystems in Julia, the documentation is excellent. So if you look at the ordinary diffeq documentation, it will clearly go through how to set up an ODE problem, how do you solve it, what options are available for solving. It also has a list of different solvers and shows you how you can swap out different solvers with essentially just a single line of code change in Julia. Then for the diffeq callbacks, documentation is similarly good. It describes quite a few ready-to-use callbacks that you can use. There's the preset time callback for the discrete events at specific times. There are also more advanced callbacks, such as those for step size control. And then kind of the cherry on top for converting from MATLAB to Julia is there's one of the pages of the documentation is a solver comparison. And so basically what it does is it lists the MATLAB solvers, and then it says what are the corresponding Julia solvers you can use. So if in MATLAB you're using the ODE45 solver, this web page will say, okay, the corresponding Julia solver is DP5. But then there are also these other solvers you might want to try that might perform better. Right? So the excellent documentation, the excellent package ecosystem, and the similar syntax between Julia and MATLAB really makes transitioning from MATLAB to Julia a breeze. So doing the actual integration, we use the matfrost package. So matfrost is a package that was developed by ASML. So thank you to ASML for developing the package and open sourcing it for the Julia community to use. And I'm going to illustrate the process of integrating Julia back into MATLAB via a live demo. So I'm going to switch over to MATLAB. All right, so here's the MATLAB workflow we're going to work with. So in this case, it's fairly minimal. That's for demonstration purposes, but the main point is we have some workflow, but there's a particular part of the workflow that's causing us grief, and we want that to be faster. But we want to make it faster without entirely destroying or disrupting our workflow. So I'm going to start this running. So in this workflow, we have some pre-processing. We're just getting inputs ready for our computation. The core computation in this workflow is this grid search function. And this grid search function is our implementation of that parameter sweep that I mentioned. And then once we have the output, we do some post-processing. In this case, we're just plotting values. But again, the main point is that we have a workflow, but there's a pain point in that workflow that we want to be better. And we want to make it better with Julia. All right, so there's our results. All right, so here I'm plotting the first state variable before the parameter sweep and after the parameter sweep. And as expected, we see that the oscillations are smaller than before. And then if we look at the elapsed time, it took about 40 seconds for this to run in MATLAB. Okay, so now we want Julia. So the first step is to take the part of the workflow that we want to improve, and we're gonna translate that into Julia. So we take the grid search function, we look at its implementation, we translate it into Julia, and we end up with a Julia function. I'm calling it grid search, just like the MATLAB function. It takes the same inputs, it does the parameter sweep, it returns the same outputs as the MATLAB version. So the same computation, just now written in Julia instead of MATLAB. And then we're going to house this function inside of a Julia package. In this case, I called the Julia package Julia model. So now we have a Julia package. It has our Julia implementation of grid search, our parameter sweep. Now we need to build a bridge using matfrost. So matfrost needs to be a dependency of our Julia package, even if the package doesn't use it at all. Because what we're going to do is we're going to instantiate our Julia package's package environment, then we're going to import matfrost, and then call matfrost.install. And what this does is it takes our Julia package and creates a MATLAB class out of that package. And in this case, and it uses the same name. So now we have a Julia model, Julia package, but now we have a Julia model MATLAB class, and this is what we'll use to interface with Julia. So this is what matfrost created for us. So now that we have that MATLAB class, now we need to start using this code to start interfacing with Julia. Now we could add this directly to the workflow itself, but again, we want to minimize disruptions to the workflow, especially if we have colleagues that are also working on this workflow simultaneously with us. So the key idea here is we want calling out to Julia to be an implementation detail from the perspective of the workflow. So we don't want the workflow to care that we're calling out to Julia. We want the workflow to work as is. So what we're going to do is we're going to create a new MATLAB function, but within that function, we're going to call out to Julia. So this MATLAB function I'm going to call grid search _ Julia. And importantly, it needs the same API as whatever function we're replacing. So I'm going to have it take the same inputs. It's going to return the same outputs. But then internally, there's not much to it, again, because all the functionality is in Julia. So what this function is going to do is I have this function getJulia, which is a function I wrote that instantiates a Julia model object. Then with that object, I can interface with Julia. So if I do jl.gridSearch right here, this grid search is not the MATLAB function. This is the grid search that I wrote in Julia, in my Julia package. So what we're doing here is we're taking our MATLAB values and we're passing them over to Julia. Julia is going to run the grid search function I defined in Julia. It'll do the parameter sweep, and then it will return a tuple of values, which is a cell array in MATLAB. So I just unpack that cell array to get the appropriate output for this function. But again, The main point to minimize disruption for the workflow is that this new function needs to have the same API, so that from the workflow's perspective, nothing changes. So let's see how this works. So I'm just going to change the one function. Importantly, I'm not changing any of the pre-processing or post-processing. I'm not changing any of the inputs or outputs. And then if I run it, I get my result. The plot looks pretty much the same as last time, maybe exactly the same. And if we look at the timing, it was 100 times faster. So from the workflow's perspective, essentially nothing changed. I called out to a new function, but didn't have to change any of the pre or post processing. But now the workflow runs 100 times faster than before. So this was a 40-second version of the parameter sweep, not the 5-hour version, so does it scale? So let's look at some other benchmarks. All right, first looking at a single ODE solve. If we just did a single ODE solve in Julia and then did the Julia MATLAB integration, that ODE solve takes 10 milliseconds, so it's twice as fast as the pure MATLAB version. I will note that there is a significant overhead to using MatFrost for the first call, but subsequent calls are faster. So a 2x speedup, that's something, but it's not the 10 to 1,000 times speedup that we were seeing with the SciML benchmarks. But again, we don't typically solve an ODE a single time. So what about the parameter sweep? You'll recall that in MATLAB, the parameter sweep with 200,000 ODE solves took about 5 hours to run. In Julia, that time dropped to less than 2 minutes. So that's a 163 times faster than the pure MATLAB version. So I think that's fast enough for this meme. I am speed, Julia is speed. So that's amazing. We took our workflow, we created a new MATLAB function that called out to Julia internally, but from the workflow's perspective, nothing really changed. But now it's 163 times faster. Okay, so it's faster, but now the other question is, are the results still good or are they garbage now? The results are still good. Here I'm plotting the first state variable before and after the parameter sweep. The MATLAB results are in red, the blue dots are the Julia results, and we see that the Julia results align with the MATLAB results. I also checked all the other state variables, and in all cases, all of the Julia MATLAB integrated results are within 1/100% compared to the MATLAB results. So we achieve the accuracy that we want for our simulations at a fraction of the computational cost. So now, if you want these speedups in your code and you're not quite sure how to start, feel free to reach out to us at GLCS. We have an approach for helping clients pinpoint these areas of concern in their MATLAB workflows. We help translate the code to Julia and reintegrate it back into MATLAB, and we ensure that we meet the accuracy and performance metrics that we need to. So unlock up to 100 times faster performance by integrating Julia. In today's example, we saw even faster than 100 times faster. Adopt Julia seamlessly. Integrate it step by step without disrupting your MATLAB workflows. So enhance the MATLAB code that you have, elevate its capabilities by integrating Julia and taking advantage of its speed and flexibility. Thank you. Yeah, so we want to see the get Julia function that I wrote in MATLAB. So yes, here it is. So basically, I made use of a persistent variable to make sure I'm not reinitializing the Julia instance every time. So I'm reusing the same Julia instance every time I call this function. But the first time, there's that overhead that I mentioned. Oh, thank you. I need to actually get rid of the Get me out of the slideshow. There we go. Okay. Persistent variable, so that way on subsequent calls to this function, I'm using the same initialization of the Julia runtime, so we're not wasting resources every time. But yeah, here is where we're actually initializing the Julia model MATLAB object. But yeah, there's nothing to it. It's like there's no parameters to. I mean, you can change the Julia version if you want, but if you have everything set up in your path, you don't need to pass anything to it. So this Julia model MATLAB class. Yeah.
Just a quick question about how long did it take to, when you call Matt Frost to install Julia model, how long does that take?
That's a good question. I don't remember off the top of my head.
It was quick, I'm assuming, or
Maybe.
it just builds a little bit of MATLAB code, right? And
right, if I remember correctly, it's order of seconds, maybe minutes,
yeah,
but
okay.
nothing terrible.
Okay, cool.
Does Matt Frost work with Linux, or is it still like only for Windows?
As far as I know, it's only supported for Windows.
Thanks.
Some of these numbers scare me a little with the performance comparisons between Julia and MATLAB. I know there's a huge difference in LAPACK and BLAS like versioning, right? MATLAB typically goes for a more numerical, stable version of LAPACK versus if Julia will use OpenBLAS by default, I think. I might be wrong on that. Could you tell me what version of each you're using for both?
I do not know what versions I'm using.
Could you just, in the MATLAB terminal, just do version space dash LAPACK. There's an I in version.
Oh, thank you. Is it capital LAPACK or lower?
That's correct, yeah. Okay, that is a faster one. Okay.
Yep.
Can you actually like create structs or more complicated types than arrays with this?
So can you create structs and arrays in Julia, are you saying?
No, like in MATLAB, can you like create structs from Julia? Like if you define a data type in Julia, can you like create it here in MATLAB?
Yeah, so one of the key things to working with Matt Frost is everything needs to be concretely typed. So like if you create a struct, you can have nested structs, and they basically get translated to MATLAB structs, but you need to concretely type it as a float 64 or an int, depending on whatever data type you have. So no abstract types.
And the function calls also need to be like typed to
Yes,
float 64.
function calls also need to be typed.
So it's down, yeah. I remember a long time ago when I was calling C code from MATLAB, it had to use these MEX files. Is that what it's using under the hood here, or is there some new fancier way of calling external code than MEX files that this is using?
Yeah, so Matt Frost does use a MEX file
oh, okay.
to work.
It's still that, okay.
All right, our final talk of the session is by Abdelazim Hussein, who's going to tell us about metaheuristics algorithms.jl. Abdelazim, please take it away.
Thank you so much. Hello everyone, welcome to my talk. My talk entitled the Metaheuristic Algorithms.gl. I'm very excited to share my new package, which has more than 150 metaheuristic algorithms. I am Abdelazim Hussein from Linköping University. So this is our agenda for today. We will start with some introduction, our motivations, some background, some few experiment, and after that practical demo, our current state, and some future work. We will start with some theoretical introduction about what is optimization. Optimization can be defined as the process of finding the most effective solutions from a set of feasible alternatives. It plays a key role in decision making and analyzing physical systems. Optimization involves identifying the optimal values for specific system attributes to minimizing or maximizing, for example, minimizing cost and completing system design. Typically, an optimization problem can be transformed easy to mathematical model. This mathematical model have fitness function, have an objective, minimizing or maximization, and have some constraints, maybe. So optimization can be classified in different ways. For example, we can categorize it to constrained or unconstrained, discrete or continuous, single objective vs multi-objective, or finally deterministic or stochastic. Also, we can divide them into main category, exact methods and meta-heuristic techniques. Exact methods includes algorithms like Newton gradient descent. It is efficient for simple and small problems. However, it is inefficient or unapplicable for high-dimensional, complex, nonlinear ones. On other side, meta-heuristic methods inspired by nature or physical law or social behaviors or human interactions aim to find near-optimal solutions in complex search spaces, don't guarantee global optimum, but can have near-optimal one. Optimization is everywhere, from economics, decision-making, feature selection, and pattern recognition. It can be also found in signal processing, photovoltaic model optimization, cloud computing, and industrial structure engineering problem. Our motivation in recent literature, most new meta-heuristic algorithms have been developed using either MATLAB or Python. Example for me, even for myself, I have developed 6 or 7 algorithms using MATLAB. I also have enhanced a lot of optimization algorithms written in Python. Despite Julia advantage in speed and numerical computing, very few meta-heuristics have been implemented in Julia over the past decades. So our goal is to create a comprehensive, unified Julia package that allows researchers, scientists, and developers to implement and benchmark algorithms, comparing their algorithm with state-of-art and winners using signal, fast, and extendable Julia-based framework. Also, we have another classification or categorization for meta-heuristic. It can be defined evolutionary or physics, chemical inspired methods, swarm inspired methods, and human-based methods. The first class, evolutionary inspired, contains genetic algorithm and differential evaluations. For physics, it contains some algorithms like simulated annealing and gravitationally search algorithm. For swarm optimization, it contains algorithms like practical swarm optimization and anti-colony optimizer, and so on. For human, containing algorithms like teaching, learning-based algorithm, and lung cancer algorithm. In Julia, we have some package like black box optimization, which is general purpose black box optimization. We have another one called metaheuristic.gl, which is lightweight, includes some classical state-of-art algorithms like particle swarm optimization, genetic algorithm, and differential evaluation. We have also someone called evaluationary.gl, which focused on evaluationary strategy like DE. We have also CMA evaluationary algorithm, or CMAES. However, in other side, for example, in Python, we have a package called MEAL Python, or meta-heuristic algorithms in Python, which contains more than 200 algorithms, which is modular and easy API. It is widely used for benchmarking new optimizers. Also, we have something like Evoli Python and Skit optimizer. So we developed a meta-heuristic algorithm, which contains, as we have said, more than 150 meta-heuristic algorithms for different categories, contain state of art, contain different mathematical type. We have added the benchmark CEC 2005, which contains different mathematical types like unimodal, multimodal, fixed dimension multimodal, and composite benchmark functions. We have also added benchmark for unconstrained real-world engineering problem, which contains around 9 functions. In lateral, we have some critical perspective and the potential objective. For example, these two papers have criticizes the meta-heuristic optimization. We agree with them. There are around 1,000 or 100 of algorithms in lateral with no real contributions. So this package, we try to competing with winners only. Every year CEC conference has some winners. So we want everyone to compete with winners. We have implemented CEC 2025 and 2014-17. We are waiting for CEC 2025 from CEC and GCO 25. We will show you some practical demo. We started with adding our package. It's not registered yet, and add lots and buy lots. After that, we have using meta-heuristic algorithm, which is the name of our package. We have some functions, some lower bound and upper bound, some max iterations, a number of populations. The result take any functions like AEO, which stands for Artificial Ecosystem Optimizers, will have been implemented by our package. After that, we give the function objective function, lower bound, upper bound, number of population, max iterations. We have the result, which is a return type, contains best fitness and best positions and history of best fitness. For example, we can show it here. We can plot now the convergence curve, which is like that. We also contains some other functions called compared algorithm. For example, if we wanted to compare our algorithm to a state of art one, for example, here we have LB and UB, which have been set to -100 and 100. We have optimization problems, not like other one. We have engineering engineering underscore F1, which is one of constrained functions exist in the package, lower bound and upper bound. This is the name of algorithms, and this is the functions. We can run it directly. So this is the output. You can compare your current algorithm or developed algorithm with the state of art. We have also contains instead of compare functions, we can replace these functions by compare with winners. And finally, we can show you, we have some documentation. For example, if we don't know what is AEO, we can ask for documentation for it, which contains 3 signatures for everyone, for every functions or every algorithm that contains a number of population, make iterations, lower bound and upper bound, some dimensions, and the objective functions. These are the common arguments, and this is return types, which has best X, best F, and history best positions. Some examples have also been included in the documentations. Practical demo can be found using this QR and this link. For current state, we have this our GitHubs, which had not that much, but around 26 stars. We have 3 contributors. Special thanks, we sincerely thanks Anki Wang from Department of Frontier Science for Advanced Environment, Tohaku University in Japan for his valuable contributions and support. We have 3 contributors. Some future work. Benchmarking against the CEC competition, as I have mentioned earlier, proceeding from CEC and GCO conferences to include them in our package. Support some new benchmarks like CEC 2022 and CEC 17, CEC 2014, including in testing and algorithm development. Why CEC matters and included standardized test suited. It is widely acceptable in meta-heuristic research community, used to fairly compare algorithms performance on various complex functions, so can overcome the criticism in the domain. Some also future work. We try to add more algorithms, winners to the package. We are trying to more documentations. We try to write some paper and publish it. Acknowledgement. This work has been supported by excellent center at Linköping Lund in Information Technology in Sweden. If you find this package useful, we would gratefully appreciate your support and contributions. Your feedback, bug report, feature suggestions, and good contributions will help us to enhance our project and benefit from the community. Feel free to open issues or pull requests on the property, on the repository. Collaboration is always welcome. If you like this project, please consider starting the repository and share it with someone who should find it useful. Yeah. Thank you so much.
Thank you for your talk. One question: do any of your algorithms support multi-objective optimization, or calculating the Pareto front for if you have multiple objectives?
No, we consider only single optimization. Okay. We now support only single objective optimization, but in near future we will try to add it to include multi and many objective functions. Yeah.
No, thank you.
Hi, I also had a question. Do you have support for inequality constraints?
I'm so sorry?
Do you have support for inequality constraints?
Yeah. Okay. I have 9. We have included here, for example, engineering F1. I can show you. This is a tension compression spring optimization problem, which contains around 4 non-equality constraints. Yeah. Yes. And you can have you can add your own problem or own.
And do you support constraints that are just lower and upper bounds, or also things like equality constraints?
Yes.
Okay, great. Thanks.
Yeah. Thank you.